typing. So then they went back to this.
Okay. Let me get hold of somebody. Oops. 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 Just hold me like. Dog is standing right there. That's why the door is, nobody's opening the door. Can you switch the. Hello. We have now second day of Sat+Smt school. Today, Subhajit Roy from IIT Kanpur going to talk about how you mix satisfiability with fuzzing. Very interesting dimension of the world of satisfiability. Okay, Subhajit, over to you.
Thanks, Ashutosh. I think. So, like the other speakers, let me also start with a demo. So I have this code here. And so this is in big vector theory, and probably you can assume what it is doing, right? So it's basically finding out two values, x and y, which are between, like x is between 5 and 9, y is between 4 and 9. And then it is trying to check whether it's trying to find out a value z such that z equals the multiplication of x and y. So if I give this program to CVC4, it immediately comes back with a very nice answer, very, very fast. Now, if you look at it, so there is this function called mul, and I have not provided the semantics of mul. And like Clark said, wherever you have functions for which you may not really understand what the semantics are, you can always abstract it out with these uninterpreted functions. And what I essentially did is that I said that let mul be this function which takes 2-bit vectors and returns out a result. Of course, I have not provided any semantics here, and the CVC4 essentially comes out with this answer where it says that maybe z must be 0. Now, if I tell you that this mul, not surprisingly, should have been multiplication, do you think this is the right answer? Not really, right? So the question is that, is there a way to make the SMT solver aware of the execution semantics of these uninterpreted functions, but perhaps with some more information? So what I'll do is, we will run this solver we have out here called Sadak, and I would provide a library which has the interpretation of this function. It's a library, so it's a binary only, but it has an execution semantics of what this function mul really means. And Sadak comes out, I'm sorry, something went wrong. For some reason, my compilation failed. So I know these things always happen when you are giving a demo. And I checked it before the demo. So oh, I'm sorry. I was giving a wrong library name. So that libc doesn't even exist. It's libt. Okay. And Sadak takes some time, does some weird stuff. And whenever it takes a bit more time, we cross our fingers. And it produces a model. So can you check whether this is right? So it's basically saying x is 7, y is 6, and the answer is something, should have been 42. Looks like it is 42. So, of course, it's underlying, it's using a randomized algorithm, a fuzzer. And so you would see that the runtimes would change depending on, sometimes it's faster, sometimes it's a bit more slower. But then it would essentially come back always with the right solution if it can. So let me then go back and try to see it even went into iteration 6. And if Sujit is watching this stream, then probably he's also crossing his fingers. And yes, it again comes back with a model, a different model. So this time it says that 6 times 5 is 30. Looks right. Right. So somehow the projection mode is not working. Let me try from here. Rotation. Okay, so let us try to understand how this tool really works and why would we even like to do something so crazy. Okay, so this idea is that we basically have, just to set this stage, we have some first order formula wherein there are some functions for which we may not have the semantics available with us. And these are functions which we call closed box functions. So these are not completely uninterpreted because we do provide a library which contains the execution semantics of this function. So we can use that library as an oracle. So we can make calls to var and we can figure out what does it return. So the problem statement is we would like to test satisfiability of first order logic constraints containing these closed box functions. Yeah, Ashutosh. Yeah. You have the binary, not the source code. They are very difficult to, so they are not really good for SMT solving. So you have to do a lot of work to really put them in a manner that it is good for solving. So things may be vectorized. You may have, well, calls to, for example, sometimes you may not even have access to the library. I'll come to it. But for example, it's a web call. So you're making a call to a web interface. So it's hosted somewhere else. So you don't even have access to that call. So all we are asking for is, and I'll really show that. So essentially, we are saying that can you have a function which has functional semantics, so which means that if I invoke it multiple times with the same input, it should keep on producing the same output, and an input-output Oracle interface is available. So we know what are the types of arguments it accepts and what is the return value it returns. That is it. And how you're making the call, I really don't care. I really don't even have to have it locally on my system. As long as I have a way of invoking it, I'm happy. Right? Okay. In fact, these can be okay. Also, so now, like, given such functions, typically what we would do is that we will abstract them out into these uninterpreted functions. We will give it to an SMT solver to solve, and the solver would produce a result. And because it's an over approximation, given that we do not really have constrained the definition of this function, we might get answers which are not right. So we might get models which are not valid models. So what is the motivation? The motivation is that nowadays we have programs which are quite complex. And for example, we have this function foo. And the function foo could be, as I said, it could be residing on the cloud, right? So you have these cloud APIs and you can make calls to these cloud APIs. They give you back some response. You have absolutely no clue what they are doing, oftentimes. And it could be an external library, some maybe proprietary library that you have linked with your application, or it could be a very complex ML model which you might have locally on your system, but then it's just too complex to reason on, right? So anything that you find either unavailable or extremely complex to reason for SMT solvers, you can throw it at R2. So there are multiple settings you can attack this problem. The first is that you can assume that this function is completely unknown. I have absolutely no idea what it is doing. And that is exactly what we do today. So we call them open programs. And then people do interesting things with it. Like, for example, they try to find out, for example, what is the maximum specification that foo can have, right? So you can come up with interesting problems, or what is the likely bugs that the program will produce. So you can come up with some interesting problem formulations and saying what could you still say, even if you know the interface of this function without really knowing what the function is really doing. We try to tackle a slightly more constrained problem where we are saying that you have an oracle access to these methods. So these are closed box functions. So you cannot really peep inside them to see what they're doing. But then you have an oracle access, so you can invoke them with some inputs and they will respond with certain outputs. And can you say something about the program with respect to that? Now, one thing I'd like to make clear, I really am not trying to analyze foo, right? So I would like to analyze my own program, which is invoking this function foo. So my primary objective is this main function that you see here, which incidentally ends up calling some closed box functions. We have some series of work along this direction. And the other thing that could happen is that these functions could even be stochastic. It could be a randomized program. And in this case, possibly you cannot really put down an assertion, a Boolean assertion, but you might want to say something about its distribution, right? So for example, what is the worst case expected value a variable can take and so on. So in this particular session, we will sort of examine this second class of problem where we will assume that we have this oracle access to this problem. I don't know if there's a way of taking that cursor out, but anyway. Okay, so a high-level way of doing that, attacking this problem, is basically using a combination of some test strategies and some proof tactics. And you could end up, and we essentially in our work, we have used fuzzing, some sort of random sampling when we're working with randomized programs. For proofs, we are primarily using SMT solving, but then there have been cases where we had to resort to computer algebra systems. So what exactly is the core idea to attack such problems, at least that we are looking at, is there's some shift in the thinking. So the idea is that can you reduce a satisfiability problem on a logical formula to a reachability problem on a program? And why would we like to do something like that? Well, then you can use these really interesting beasts that have come up in the last few years called fuzzers to solve this problem. So this to me is a very interesting paradigm shift, because for a good part of the last century and this century, we have been trying to take programs and model them into logical formulae and trying to solve this logical formulae to say what the program is doing. Here we are going the other direction. We are taking logical formulae and saying we want to reason on them, and we are turning them down into programs, simply because we now have very, very strong tools to reason on programs directly. So going by the same template that Clark used yesterday, so we can have certain eager strategies to solving these problems, or there can be some lazy strategies. So we have really built tools to attack all these class of problems. So we have this tool called Colossus, which essentially does fuzzing. The problem is that when you're using a fuzzer, they are typically slower than these SMT solvers. The SMT solvers have been really tuned to work very well on the problems of realistic problems that we see today. So some of the optimizations that you need to do is to try to not use the fuzz solver a lot. To that end, we have this tool called Colossus, which essentially tries to find out if we really need fuzzing. So in case you think that you can do away with fuzzing, it does not even call the fuzz solver. So it tries to use an SMT solver, only needed if it calls fuzzing. We have another tool called Achar. So Achar essentially does fuzzing for fragments which need to be sent to the fuzzer. So it tries to divide the function in the formula into parts which can be reasoned completely by an SMT solver, and parts which would need a fuzzer. And then I will focus most of the time, spend most of the time on a lazy strategy that we call Sadhak, which essentially is something that we just saw some time back. So coming to Colossus, so what the line of attack Colossus uses is it takes a logical formula and it creates an under approximation of the formula. So it concretizes some of the variables in the formula and tries to say that can I still find a solution with this partial assignment. If the solver turns out to say SAT, in that case, it means that the solution that you get is indeed a valid solution. In that case, it returns a solution and it does not even try to invoke the fuzzer. However, if it turns out to be unsat, because you're looking at an under approximation, it can happen that it's an under approximation of the solution space. So a satisfying solution might be lurking outside. So in that case, we compile the program into a program, compile the logical formula into a program, and then send it to a fuzz solver. So we deployed this strategy in our symbolic execution engine called Colossus. And it's a very nice fit for symbolic execution because symbolic execution has this inherent mechanism called concretization, which allows you to reason on these black box functions. But we showed that if we use a slightly more sophisticated reasoning on these concretizations, something we call deferred concretization, you can actually do much better. So there are program paths you would have lost to concretization, which you could recover. And we, like over baselines, like very strong baselines like Clee, we were able to get really impressive improvements in coverage. The next eager strategy that we investigated was our tool called Achar, so which tries to fuzz only parts of the formula that need to be fuzzed. So what Achar really does is it creates a disjunctive partitioning of the formula, a part which can be completely reasoned on using an SMT solver, and part which must use a fuzzer to reason on. So, this essentially is sent to the part which can be reasoned with the SMT solver is sent to the solver, SMT solver. The part which goes to the fuzzer goes to the fuzzer, and if both of them say satisfiable, then we are done. We deployed Achar in a tool to find invariants, and we call them almost correct invariants because there is an element of testing here. So we may not be completely sure of the invariant is indeed an invariant. But then we found that in most cases, the invariant that it dishes out is indeed a correct invariant. So the idea is that we use this very standard teacher-learner setting for finding invariants, and the backend of the reach oracle in this case is our solver. It uses an array of tools. It can use a SMT solver like Z3 or CBC5. It can use fuzz engines like AFL and HonkFuzz. It can even use Colossus that we just saw some time back. And we introduced this notion of what we call proof fuzzing. The idea is that instead of trying to fuzz programs to find bugs, you can try to fuzz proofs of program correctness and try to find violations of the proof, right? So find out instances where the proof does not hold. And maybe that you can use. So we could write a theorem saying that, okay, if a reachability problem in the program, like you can decide on a reachability problem in the program, then you can actually say that the proof is correct, or a given invariant is indeed a correct invariant. Now with this setting, I'll come to our latest work in this direction, which was Sadak. So Sadak employs a lazy strategy. And the purpose of Sadak was to build a general purpose SMT solver which can reason on such closed box elements. So with Sadak, we introduced a new theory, a new SMT theory, which we called the CB of closed box functions, or CB functions. And to support these closed box functions in SMT solvers, and we implemented an algorithm called conflict-driven fuzz loop, CDFL, just to make sure it doesn't rhyme similar to anything in the SMT world. And we use this function to talk about, to reason on these CB constraints. So at a high level, what is going on? So this is something we already saw yesterday from Clark. And this is the very famous Nelson open loop. So the idea is that you have the boss sitting there in the Oval Office, the SAT solver, and the SAT solver essentially starts making queries to the theory solver using some partial assignments. and the theory solver sends back with conflicts. And these two solvers exchange propositional lemmas with each other to converge to a solution, right? Now I'll take the same structure and I'll show what Sadak really does. So Sadak replaces the SAT solver by a fuzz solver. It replaces the decision theories or the theory solvers by SMT solver, by a SMT solver completely, and the rest of it remains exactly the same. It's very similar to the Nelson open loop. So given that we are now talking to an SMT solver, instead of propositional lemmas, we can exchange much more richer lemmas to understand where the first solver and the SMT solver can understand each other. However, this also comes with a cost. The cost is that the first solver and the SMT solver speak different languages. So there has to be a translator, somebody sitting who says what you really mean, right? Because the first solver is operating in this the domain world, the domain of logic, and the SMT solver is sitting in the domain of logic, and the first solver is really executing programs. So it really needs to know what does it mean to execute a certain instruction. So the question is, how do you really make them talk to each other? So in effect, what Sadak does is creates a synergistic combination of SMT solving and fuzzing. And as we just saw some time back, Sadak essentially accepts a logic fragment in a dialect of SMT-lib, and also an access to the closed box elements, right? It could be a library, it could be a invocation, maybe an RPC call or whatever you wish. And together with that, Sadak can produce solutions which are satisfying solutions. So the disclaimer is Sadak is sound but not complete. So it may not be, so if it produces a satisfying model, it indeed is a valid model. However, there's no guarantee it will produce one. So this is the SMT-lib encoding of a problem in Sadak's theory. So we essentially introduced this new keyword called declare CB, which allows you to declare a closed box function. And whenever you declare a CB function, you also have to provide a supporting library, supporting access to calling this. So this defines the Oracle interface. It defines the interface to the CB function, and you have to have a matching. You have to have a matching library or a call which has exactly the same signature, right? Now, the CB theory essentially looks like any regular theory, but we have these two new things. We have FCB, which is this set of sorted closed box functions. And we also have the schema R, which we use to translate between sorts and expressions between the solver and the. So remember, I talked about that, given that these two solvers talk different languages, we have to have a translator. So R is basically the table for the translator. So the translator looks up the R table to find out how do you translate something in the logic world to something in the real executable world. So let's look at this example, and I'll try to walk you through as to how Sadak really works. So in this case, we are assuming that isPow2 is some uninterpreted function. I really don't care what it is, but f is a closed box function, right? And we have a supporting call to f available with us. So to begin with, it proceeds very similar to how Nelson Open proceeds. It does purification. It separates the theory constraints. And then it does separation. It essentially separates out all the SMT terms from the fuzz terms or the CB terms, right? So in this particular setting, we only had z equals f of xy as the CB term. And I'm just writing it as FCB because it is lying with the CB solver or the fuzz solver. On the other hand, the SMT solver is given an uninterpreted model of f, right? So it just knows there is some uninterpreted function FUF sitting in the SMT solver, but really doesn't know much about it or anything about it. So once this is done, the CDFL loop starts. To begin with, the fuzz engine tries to propose a partial model. It tries to go do fuzzing and try to identify a model for X, Y, and Z, which satisfies the semantics of the execution semantics of the closed box function. Now, this model is propagated down to the SMT engine. Now, the SMT engine realizes that this partial model doesn't work because there is a conflict with X is greater than Y, because X has to be greater than Y, but here X and Y are both 0. So in this case, the engine realizes that this term, X is greater than Y, seems to be very relevant for the first solver. So it steals this term from the SMT engine into its own fuzz engine. At the same time, now that we know that the CB solver has produced X equals Y, Y equals X equals 0, Y equals 0, Z equals 0. So the SMT solver learns something more about the uninterpreted function, saying that, oh, now I know that when you invoke F with 0, 0, it produces a result 0. So now both the solvers know a lot more than what they knew earlier, and the loop continues. So this time, maybe the first solver, it cannot produce the same model again because X is greater than Y prevents it from producing X equal to 0, Y equal to 0, Z equals 0. But then it says, oh, well, now let me change it to X equals 1, Y equals 0, Z equals 0. It again propagated back to the SMT engine. And now you find a conflict again. And it says, well, Z must be greater than 255. This is propagated back, and we learned it back into the fuzz engine. And a new UF term is learned by the SMT engine in the process. The same thing continues. Now it produces a value of Z which is greater than 255. Again, it propagates back to the SMT engine. Again, it finds a conflict. This conflict lets it steal this new term back into the fuzz engine. Again, it learns a new UF term. In the fourth iteration, I'll be getting lucky now. So we propagate this back, and we get a consistent result. So now we get a result where a first solver proposed something, and the SMT solver was pretty happy with it. And then they both shake hands and say, well, this must be a valid solution. Right? So, okay, so this is the final model that we assemble, assembling the evaluations from the solutions both from the fuzz engine and the SMT engine into a model over all the variables. And you can see this was the interpretation of F. So how does Sadak really work? So at least the schematic of Sadak. So Sadak has this compiler which takes a SMT formula, and using the translation schema, it translates it into a program. And the program is fuzzed. And there is a theorem which says that if certain states in the program are reachable, then the formula must be satisfiable. And if it's able to find a reachability, it successfully finds a reachability to that particular location, it produces a model, right? So this is how the Sadak engine is architected. The fuzz engine is architected. So, right, and this is the whole high-level view of the whole scheme. Yeah, Kuldeep. We are taking a term from the SMT side and pulling it into the fuzz side, yes. So what I mean by term is a first order term. No, we are looking at quantifier free at the moment, at least. Quantifies, if you do, that's what you mean? Yes, yes, very good question. So there are two parts of it. So even if you do not have the translator, we have a base mechanism of still propagating, learning something out of it, right? I mean, we can still, like, for example, you start learning at least the UF terms. You know that certain valuations are correct on the SMT side. So we can still give you something. But the better translator you provide us, we can do that much more better, right? So this translation scheme R is, it decides how rich are the lemmas that these two solvers can exchange. So richer the set of translations you can provide us, the Sadak can really work better. We can still do something out of the box, but may not be very good. So we already provide something for bit vectors, something partial for integers, but I mean, you are free to write your own Rs. Yeah. Not yet. Not yet, future work. But then you can think of a model in the programming languages, right? So you can think of there being at least finite size arrays. You can think about having, so yeah, so it's up to the R that you decide. So you can come up with what this R would look like. What would this translation look like for you? And accordingly, you can pull in things here and there. Quantifiers become interesting because quantifiers would need you to have possibly loops in the program, right? Makes fuzzing a little more challenging. But yeah, I mean, that is where we are. At the moment, we are looking at QF fragments. But having said that, I mean, we still believe currently we are really not looking so much at, I mean, we are doing some work. We are trying to extend the logic that can be used with Sadak, but then currently a big focus that we already we are really pursuing very hard is, can we improve the fuzz engine? And after 5 years, we realized that, well, probably we are not doing the right thing when we were doing fuzzing. So we have some good ideas and we are trying to make the fuzz engine much faster. Perhaps maybe the next Sat+Smt meeting, I may be able to tell you more about it. But if that happens, then we will be able to even support these other theories much better, because the fuzzing engine would have improved a lot more. We just pull all the CB terms, whichever functions, wherever we have functions, which are CB functions, we pull them to the CB side, everything else goes to the SMT side. And that it learns it dynamically. It starts identifying, oh, this is also relevant to me, and that happens within the CDFL loop. Yeah. Yeah, so maybe I should have added a slide on that. I don't have a slide on that, but R is like simply saying that, for example, you have to have translations for all your sorts and all your expressions, right? So like, for example, for sorts, whenever you say, let's say BB32, so you might say that is UInt32, right? BB16, UInt16. So you are mapping logic sorts into program types. And the other is about expressions. The same thing goes for expressions. Whenever you see add, so you have BB add, so you may just say it's plus in the language, right? And you're free to define your own semantics. You might want to even write some functions yourself that you can add to R. So we don't care as long as we can execute it. Translation has to be correct. That is your problem. Yeah, agreed. Yes. Yeah.
Seems like you're giving fuzz engine the minimum amount at the beginning.
Yes.
Why not give it the maximum?
Excellent idea. So that is what the eager approaches were doing. They were just giving everything. And they said, you figure it out. I don't care. Right. So there are pluses and minuses. Again, like you said, I mean, eager and lazy strategies are really not comparable. There are cases where that does really well. But there are most of the cases we found the lazy strategy works well. Fuzzer, the fuzzer. So fuzzer is slow, at least at the moment, till we make it fast. So yeah. Excellent question. Yes, this would be much more amenable to, like, you can push them into the CB side and try to reason on them. Both fuzzers, both are not so hard because it is anyway doing some sort of evolutionary search. So it identifies much more complex functions much easier than really reasoning on them. So I would assume that would be much easier. I'll come to it. So yeah. Yeah, so you can think of the formula has been split into two parts, and both the parts have to be satisfiable, and on the interface variables, you must have agreement. And if that happens, then the whole formula is solved, right? So that is exactly what's happening. So the first solver is solving its own part, along with the interface equalities or interface variables. And the SMT solver is trying to complete the partial assignment, maintaining the same values of the interface variables. Yeah, we saw that, right? So you are pulling those terms into the first solver. And these are not the terms only from your initial search, like in your initial formula. This could be lemmas that were learned during SMT solving, right? While SMT solving, you might have discovered some lemmas, and they can also be pulled into the first solver. So they may be more refined, may have more cleaner understanding of the formula. So they will all get pulled in. They may, if required, will get pulled into the first solver. Thanks for the questions. Right. So now essentially, so the fuzz engine proposes partial model with the SMT solver tries to agree on. If it cannot, then it produces a conflict, and you do some sort of conflict analysis and find out the reason, learning a lemma in the process. And if you find things are consistent, we produce a model. And this is something we call CDFL. This is our conflict-driven fuzz loop. Okay, now coming to Supratik's question. So there was this tool called Delphi. So it was some very interesting story. We were like a month or a month and a half from submitting our work after almost 2 years of really hard work and fighting out things. And then we see this paper appearing in BMKI, and we were like, man. So my student, like Sujit, who was a really good student, I mean, he was working on it, and he really got frustrated that, oh, come on, I mean, we got scooped. But then we tried to, but it really worked because it sort of turned out to be a good baseline that we could compete against. And before getting into the results, let me tell what Delphi does differently. So as you saw in our figure, the first solver was the boss, right? And it was sort of proposing stuff, and the theory solver, the SMT solver, was trying to complete them. What Delphi does is it does things differently. It makes the SMT solver the boss, right? So it has an SMT solver, and the SMT solver tries to propose these completions, and it doesn't use a fuzzer. Instead, it uses just the function oracle. Because it has an assignment now, it can just call the function and check whether the assignment was correct, right? And if the assignment was correct, all good. If not, you learn a lemma saying you know something more about the function. So all its effort was not to really, it was to just to understand what this function must be. And it was trying to learn enough lemmas about the function for the SMT solver to be able to reason about it sufficiently. So it uses, it's a very different approach. Again, I would say these approaches are incomparable. There are cases where Delphi does better. And Delphi does better when the calls to the function oracle are expensive, right? So because I would not like to fuzz such a function which have very expensive oracle calls. But this is the comparison that we have over our benchmark. This includes both the Delphi benchmarks as well as many that we wrote, and the benchmark suite is also available for you to use if you want. Most of them were constructed from Seiger's benchmarks. We removed the function, we removed the grammar and what the function would say. There were some taken from path conditions in symbolic execution engines and stuff, remove the interpretations of these functions, and we try to see whether we can do well. So we see that. So let me explain the lines. The first line that you see, so Delphi comes with two modes. It has the bit blast mode and the SMT mode. The SMT mode is where they use SMT solver to solve stuff. The bit blast mode, they just bit blast everything to SAT and just resort to using a pure SAT solver. So the first line that you see is the SMT mode, and you can see that the blue line is the bit blast mode of Delphi, which is much faster than the SMT mode, at least on their benchmarks. Sadak provides both the options, like what Clark said. Why don't you just eagerly fuzz everything? Sadak provides a mode for that. You can give a fuzz only flag, and it can do an eager inlining for you, and it can just fuzz everything. And it also has this lazy algorithm built in. So the red line is the fuzz only mode. This does this eager strategy. It just tries to push everything to fuzzing. And the green, something we are proud of, is the lazy strategy, which does really, really well. Okay, so the work did get was noticed by the community, and we were invited to present it in this MIT peer review. And there were some very kind words provided to us from the review committee. So it was one of 9 papers that were invited there. And anyway, so the tool is available. I would encourage all of you to please try it out. We have a Docker container, so it's very easy to get started and running it. It's still, I would say, a research prototype, so you might find rough edges, but please let us know. And thanks to Sujit for this really wonderful work, and at the same time letting me steal his slides. So with that, I'll like to end my talk, and I'll be very happy to answer any more questions. What is my web page? Don't talk about my it's terrible right now. I'll probably fix it sometime. It's on Sujit Singh, but I have you can, if you just click on this, you'll be able to see find the link. Yeah. Oh, sorry. Oh, I see. Yeah. So, I mean, I think the main thing is it doesn't use a fuzzer. So it doesn't really care so much about the function Oracle calls. It says let the SMT solver learn more about it as it goes on demand, whatever it wants to learn.
Yeah, like your idea. There's a lot of the function oracle has many values. Right?
Exactly. That's the bottleneck that Delphi gets stuck in. But again, I mean, the good thing about Delphi, as I said, is the cost, right? So the SMT solver is making very wise decisions as to what is the query it needs to make to the fuzzer, to the Oracle. But we madly fuzz it and we say, well, what can you tell us? Yes, very much so, very much so. But having said that, I mean, it's not that it's only the SMT solver learns everything. Both of them learn something, right? So it's the fuzzer also learns something, the SMT solver also learns something, and together with this improved knowledge, they try to converge on a solution. Yeah. The inside proof is going to come from the SMT solver using those learnings, the F function understandings it has got so far. So using them, it tries to find answer. Absolutely. 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 Fuzzer will not be able to lead, but it can happen that because it's learning those function like it's learning those point-wise valuations of the function call, the SMT solver. So using those, it might be able to drive a contradiction. Maybe. If there are finite number of them, yes. So it may be able to enumerate all of them and drive a contradiction or say none of them. Sort of. Unsat cases, good question. Hard to say. I think both of them sort of would resolve to the same thing, modulo the cost of the function calls. They'll end up sort of doing very similar things. But again, the thing is that yeah, it's difficult to say. So in this case, what's happening is the SMT solver is sort of proposing the decisions. Like it's saying that, okay, well, why don't you try out with this partial solution? But in the other case, the first solver was proposing the decisions because the idea was that like finding a partial solution on the CB functions is harder. So let me get that out of the way first, and then the rest will follow. Yeah, but at the end of the day, you'll end up enumerating all of them. So eventually, yeah, it'll sort of boil down to that. There were most of them were satisfiable, I would say. Yeah. Hmm.
Because they're built on top of some.
AFL. Yeah.
Okay, so I'm still missing. Why couldn't we just take the SMT formula, file it into a binary, just run the FL?
That's the fuzz only approach. That's the eager approach. That the problem is the fuzzer is way slower than SMT solving, at least at the moment.
But is it, I mean, every call, every time the fuzzer invokes the binary, it's very fast, right? It'll do it like 10
Yeah, but then it sort of madly tries them out. So it's very difficult to. There is a guidance, but then it's sort of empirical guidance that you use. No, so you have to define the theory. So you can come up with your own theory. Okay, that's a good question. How do you add new theories to Sadak? Clark showed us how to do it in CVC5, so I should follow. The trick to that is to add for the theory, whatever theory you want to support. Of course, you have to have that theory in CVC5 for sure. It's built on top of CVC4. Thanks to Clark as well and his group for a lot of help that we got from them. I mean, the queries were resolved really, really quickly for us. But coming back to your question. Right. So the theory has to be supported by the base solver, that is CBC5 or CBC4 in our case. And then you have to say that how can I take it and lift it into Sadak, right? Now, well, it works out of the box. If you just have a theory in CBC5, we can just do something about it and we can still learn something if you just give us the interfaces, the oracle interfaces, the CB interfaces. But if you can give us this translation schema, we can do much better. So then if you really are serious about your theory, then you would sit back and painstakingly write down that R schema, which will say that for every thing in the logic world, how do you take it and take it to the bare metal execution world, right? And once you have done that, you should be able to do it very efficiently with Sadak.
lazy approach works for the reason that most CGAR approaches work. You don't need all the information.
Absolutely, absolutely. That and we are keeping the information from the I would say the harder part of stuff. So the fuzzer is doing the more difficult job. I don't want to really overwhelm it with too many things, so we try to keep that in. Yes, yes. It builds in, that's why it's slow, right? It builds a new program, it compiles that program and starts it off and starts fuzzing it. There are some optimizations we do, like we have found that there is some learning that you do in SMT, right? Where you take lemmas and those lemmas help you solve, even if you do incremental learning, even if you add a new constraint later, those lemmas really help you even then. So we do something similar. So here it boils down to the seeds that the fuzzer has. So we preserve those seeds and we sort of push it and pop it in some manner that we can make use of those in the next runs. Because things are only getting added to the fuzz solver, things are not getting removed. So we are not supporting push pops at the moment, but that can also be supported. It's just that you have to remove, you have to keep a stack of those seeds. So there is some learning, even at least some incremental learning that even the fuzzer is doing. I'm sorry, I couldn't hear you. Huh. No, we don't cache any code. No, we throw them away for the next run. But good idea if you're supporting like things like push pops and all, maybe they can come handy. Not bad. Okay, I think, yeah. It's a chain of if, yeah, it's mostly that. And that we found is not a good way of doing things. And that is what we're trying to fix, right? Okay, so this is some future work we're doing currently. We think that that is not the right way of doing things. Let there be light. No, it only grows in size. You're thinking right. If you can manage that, if you can do the, yeah, you don't do any of those things because the compilation is still one part of it, but the fuzzer is still slow, that's just during its execution. So bottleneck is not so much in the compilation, but please, I will happy to collaborate with you, like if you can build in. But these are tricky things to do. So you have to maintain a code cache, you have to like update it, see what has changed, what has not. So sometimes they do not fetch enough benefits overall. Yeah, but yeah, sure, things can be done. Okay, thank you for the questions. I mean, it was really lovely presenting here. Thank you so much, and like of course, I'll be happy to answer any more questions. So this is still under active development and active research. So we'll be happy for collaborations and anything that you think it can be useful for, and what you think can be added to this. Thank you all. Bye. I guess so. So can I announce? Yeah, it's coffee break. So I think we can break out for coffee. It's there, right? Same place that as yesterday. I had the mic, so I thought, why not? Yeah, yeah. I think basically it's random testing.
So you just took the same question.
Hello, hello. Hey, so let's get started. It's my great pleasure to introduce our invited speaker for the day-long tutorial today, Kiran Makrish. Kiran Makrish is a Royal Academy of Engineering Research Fellow working at the University of Glasgow. His research covers the design, implementation, and evaluation of practical algorithms for hard combinatorial problems with a particular focus on providing correctness and reliability alongside high performance. I know Kiran because we often attend similar conferences, and usually when it comes to the awards, he gets all the awards. So Kiran received the ACP Doctoral Research Award in 2018 for his PhD thesis. He received the Early Career Research Award this year at CP 2023. He his paper at AAA 2022 was awarded Distinguished Paper Award. This year, his paper at CP 2013 won the Best Paper Award. So we are very happy that Kiran accepted our invite, and we'll be talking today about his work that has spanned on graphs and combinatorial solving. So, Kiran.
Thank you. Thank you. It's very nice to be here. It's my first time in India. So I'm going to be talking about finding little graphs inside big graphs. This is a problem I've been working on since just before I started my PhD. So I did a summer internship with Patrick Prosser on this, and I was hooked. And I've been trying to solve this problem ever since. So to give you an example, this is a problem we call subgraph isomorphism. I'm going to give you a little graph on the left, which we call a pattern, and a bigger graph on the right, which we call the target. And all you have to do is find the little graph inside the big graph. So this is fairly easy. Here is one way we can do it. Some of you may note there is an extra edge in the target graph. This is what we call a non-induced subgraph finding problem. So non-induced means you're allowed to have extra edges. There is another version of a problem called induced, where you are not allowed to have extra edges. In applications, people care about both versions of a problem, so I will talk about both today. This is not the only solution to the problem. For example, we can swap the pink and green vertices around. Or there are another set of solutions up here. So we can have the green and pink vertices either around. There are two places for the blue vertex there. There's another solution, or another set of solutions, I should say. And another set of solutions down there. Even more solutions, even more. I have definitely missed at least some of the solutions in this picture. If you want to try and work out how many I've forgotten, that could be fun. This is a hard problem, but somehow in this particular case, finding one solution seems to be very easy. The difficult thing is being sure that you found all of them. Here is another subgraph finding problem. This is called maximum common induced subgraph. So I'm going to give you two graphs, and you have to tell me, what do these graphs have in common? So what's the biggest subgraph that you can find in both cases? This problem is always induced, because in the non-induced case, you would just say, okay, I'm going to take all of the vertices and none of the edges. In this particular case, the biggest thing we can find in common is here. So all but one vertex. Except maximum common induced subgraph comes from applications. It turns out chemists care really deeply about this. And if you show this solution to a chemist, they will be very upset. And they will say, this is not a graph. According to a chemist, a graph has to be connected. And this is not connected. So the problem they actually want to solve is called maximum common induced connected subgraph, which only has a smaller solution and which is quite a bit harder to solve in practice. They won't tell you this. They will just say, find me a subgraph. To them, obviously, all graphs are connected, because why would you not have bonds between atoms in a molecule? Here's another easier problem. So I give you a graph. A clique is a subset of vertices where everything in this subset is adjacent to everything else. So it's a set of people where everybody in the set is friends with everybody else, and you want to find the biggest one possible. Can anybody see it? Yeah, so there's a fork leak there. The question is whether there's anything bigger. In this case, I claim there isn't. I might be lying to you. It turns out these subgraph problems occur an awful lot in practice. Chemists care a lot. So in this case, the graphs come from molecules, so they're actually labeled. So we might have carbon and hydrogen vertices, for example. Also biochemistry, where the graphs tend to represent proteins. These are a bit more complicated. These tend to give you very big graphs. Again, drug design, a quite popular problem. There is a database you can go and download which contains every compound that chemists have ever studied. And somebody who is looking to design a new drug might ask you to find me candidates in this database that have something that is the following shape because they think it will bind on and do something to a disease. And also does not contain any of the following shapes because we think those will probably kill people. And the question here is, does a compound already exist that might be usable to develop a drug? For a long time, people tried to use graph problems to solve computer vision. This has become less popular now that machine learning can actually solve computer vision problems, but this was an interesting line of work for a while. It does work for problems like character recognition, not so much for telling you whether there's a cat in a picture. Compilers do a lot of graph rewriting. It turns out if you're generating machine code, you want to be able to represent your code as a graph and then match patterns that you might have machine code instructions for, or to rewrite a program into something that will run more efficiently. Plagiarism is another interesting one. If you have students who think that they can rename their variables and get away with submitting somebody else's work as their source code, it turns out you can transform programs into a graph and then do graph similarity measures, and it's really good at catching people who are cheating. This also shows up in malware detection. People like to write code that rewrites itself so that it's harder to detect. Again, you can turn this into a graph problem. Remove all the unnecessary information and you can somehow capture the structure of malware using graph matching. Another thing I've worked on is livestock epidemiology, so finding diseases in cows. It turns out that the UK has a lot of farms that trade animals between each other, and the government is quite concerned about the spread of animal diseases between farms. In the UK, we have records of every transfer between farms that are made for any kind of animal. And you can start querying this data and you can find out all sorts of interesting things, including, for example, one cow that was sold to the same farm 100 times. This might be indicating that something slightly suspicious is going on. Somebody not paying their taxes, possibly. But another very interesting and bizarre paper I came across that cites some of what I did was designing mechanical lock systems. I don't fully understand this, but there are some limitations on how you can design certain kinds of keys for locks, and they turn the problem into a graph problem. And we're able to design new kinds of keys or show that keys of certain properties didn't exist. Now here's the problem. In theory, finding subgraphs in a graph is hard. Counting subgraphs in a graph is also hard, and even approximately finding or counting things in graphs is hard. Basically, any measure of hardness that you can come up with, the clique problem is probably hard with respect to that measure. But we are solving these problems anyway. Just like how SMT is very good at solving some kinds of scheduling and resource allocation and verification problems, we have very good solving algorithms for subgraph finding. There are real applications running in the real world that are solving thousands of subgraph isomorphism queries per second. So doing this in real time on real data. And just to give you an idea of the gap between theory and practice, so all pairs shortest path is a polynomial time solvable problem. Clique is theoretically one of the hardest problems in NP that there is. It's non-approximable, etc. We can solve maximum clique on larger graphs than we can solve all pairs shortest paths, subject to a whole lot of terms and conditions. But just to give you an idea, theoretical hardness does not tell you anything. On the other hand, maximum common subgraph, we can't do it. A PhD student who was working with improved the state of the art for maximum common subgraph by 2 orders of magnitude in an algorithm. We thought, this is a really, really good result. This is a problem people really care about. 2 orders of magnitude took us from being able to solve a problem on a graph with 30 vertices to about 40 vertices. Yeah, the graphs that people care about really have 10,000 vertices, so we're a little way off on that one. Maximum common subgraph is just hard. The other problem here is people don't actually want to solve subgraph isomorphism in practice. They'll tell you, oh yes, I want to find a subgraph isomorphism. But what they're really looking for is quite often something else. Some examples. As a mathematician, when I draw a graph, I draw some dots and I put some lines between them. In applications, for example, in chemistry, the dots might say carbon or hydrogen or uranium. And the rule is that you can only map a carbon atom to a carbon atom, a hydrogen atom to a hydrogen atom, and so on. So we're dealing with labels on vertices, also possibly labels on edges in some applications, so you have to match the labels on the edges as well. And there are some notions of broader compatibility functions. So we might say, okay, if you have a red vertex in the pattern, you can map it to either a red vertex or a blue vertex in the target graph, whereas green vertices can only be mapped to green vertices. Turns out people want to be able to give these arbitrarily complicated expressions on what you're allowed to do. Sometimes edges have directions on them. So if you do a road map, for example, it might be that there's a road going in one direction, but not the other way if you have a one-way street. Another example is the livestock trading graphs. They all have directions on, so it is farmer A sells to farmer B, and there is an edge going in one direction. If you have an edge going backwards and forwards between 2 farms that are selling to each other a lot, sometimes it's an indication that something interesting is happening. Sometimes you will have more than one edge between vertices. This can be quite common. For example, if you represent every single trade of an animal as an edge, you could have thousands of edges between vertices. And then the question of what exactly a subgraph is depends. Usually you have to have at least as many edges when you're mapping, but sometimes people want exactly the same number of edges and so on. Some people don't really like the idea that an edge can only go between 2 vertices, and they want to have edges that go between more than 2 vertices. These are called hyperedges. Recently, a group in Vienna have started looking for what they call partially defined graphs, where they will tell you that some of the edges are definitely present, some of the edges are definitely not present, and some of the edges we don't know. And then again, they have their own rules for what a subgraph means when you're looking at partially defined graphs. This is quite fun because it's a notion of approximate subgraph matching where the approximation is only in very specific places. It also turns out sometimes you're allowed to map 2 vertices to the same place. So you're not necessarily looking for an injective mapping. This is also called homomorphism finding. And I came across a slightly strange notion of local injectivity, which roughly speaking means you're allowed to overlap the graph, but only if you're overlapping bits in the pattern that are far apart. And again, all of these occur in practice. So if you're designing software, you need to think about all of these and be able to support all of them. And the thing that everybody forgets, sometimes vertices have an edge to themselves. This is called a loop. Probably nearly every solver out there has bugs on loops at some point because we always forget about these. Somehow these complicate everything. And then when you start talking about multi-edges and hyper-edges and induced versus non-induced, it becomes very confusing as to what loops mean. So everything in these slides should be understood to say, except that loops do something special, which I'm not going to tell you about because they just make things more complicated. Today, I'm pretending that loops don't exist. I should not be doing this. And here's the other thing. People don't just want to know yes or no, is there a graph? They might want to be given all of the solutions or a count of the solutions. They might want to know, you give me a representative sample of the solutions, things like this. So we're not just solving a yes-no problem here in practice. In particular, in theory, people talk about decision problems where the answer is yes or no. If you'd say to somebody, yes, this graph occurs, and I'm not going to tell you where it is, they will be very upset with you. Almost always people actually want a witness saying, okay, this specifically is where you can find the graph. Okay, how do we actually solve these problems in practice? So there are two design philosophies here. The first is what I call growing a connected component graph. The idea is you pick a vertex in your pattern graph, and you say, okay, I'm going to guess that this pattern graph is going to go here in this target graph. And then what you do is you start looking at the neighbors of the pattern vertex, and they say, okay, these neighbors have to go to neighbors of wherever I map the pattern vertex in the target graph. And the idea is you keep on trying to grow and grow and grow until you get a solution. And if it doesn't work, then you backtrack and you try one of your other guesses. There are a lot of popular solvers based upon this. Particular VF2 is the classic algorithm. VF2 has a very good marketing department, so if you Google for subgraph isomorphism, you'll probably find VF2 first. They have a newer version, VF3. There are related algorithms built on top of it, RI, TurboISO, and so on. The advantage of these algorithms is they are very fast to start up. So you give them a problem instance, and if you're lucky, then after 1/10 of a millisecond, they will just say, yes, here is your solution. The difficulty of these algorithms is they are extremely bad on some other instances, and I'll tell you more about this later on. And even on some instances that would be very, very easy for a human to solve, these algorithms struggle. The other approach is based upon constraint programming. This is what I'm going to talk about today. The idea here is we're going to build up a mapping from a pattern graph to the target graph, and we're going to do this using constraints. So constraint programming, for those of you who haven't heard about it, is like Boolean satisfiability, except we're not just dealing with Booleans. So we have this notion of, for example, integer variables. I will build up a constraint programming model and explain to you how this works. There are really two families of solvers using constraint programming. There is Christine Solnen's group, who produces a solver called LAD, and there is my baby, the Glasgow subgraph solver. What happens is every few years, Christine has a good idea, implements it, and she has the best subgraph isomorphism solver in the world. And then I see the paper, I steal her idea, I make it run faster by doing less work, and then I have the best solver in the world. So I think currently I'm winning, but Christine is about to publish a paper where she will temporarily steal my crown from me until I go and take her ideas and make them run faster. Constraint programming, it gives you much more consistent performance. It performs consistently well on easy instances, and it is much, much better on hard instances. And I will explain what I mean by this. Yeah, so you can download this and play with it if you want. We won't be using this solver for the hands-on lab this afternoon. Instead, I will be getting you to write your own solver for a slightly simpler problem. But if you do want to play, if you do ever have any graph problems to solve, then please do give this a try. It's a fairly flexible solver. It does support lots of variants of the problem, so induced, non-induced, etc. It does have special algorithms for clique finding and maximum common subgraph. And I can absolutely guarantee that there are no bugs in my solver. Or rather, I can guarantee that if you turn on the proof logging feature, if the solver ever produces a wrong answer, there is a way of detecting it. And again, I will explain some more of this probably this afternoon. We're quite lucky for subgraph isomorphism to have a large set of benchmark instances. These are maintained by Christine Solnon. We have a set of over 14,000 benchmark instances. At this point, we can solve nearly all of the instances in this set. There are maybe a few hundred instances left that we haven't been able to solve yet. A lot of these instances these days we consider to be very easy, but if you go back 20 years, then nearly everything in this data set would have been pretty much impossible to solve. Again, we're seeing, just like in SAT solving, we're seeing huge progress in what we can do to solve these problems in practice. Okay, is my algorithm any good? Is my solver the best in the world? What I'm showing you here is something called a cumulative plot. You might hear these called empirical cumulative distribution functions. In the SAT community, you will also see something called a cactus plot, which is this with the axes reversed. If any of you are ever going to do a cactus plot, please don't swap your axes around. Cumulative plots are objectively the correct way of doing things. This is a matter of some debate in the community, but I'll explain why after I've explained how you read the plot. So what I have here is I have a line for each of the 4 different solving algorithms. On my y-axis, I have number of instances solved. On my x-axis, I have runtime in milliseconds using a log scale. So I'm running up to 1,000 seconds here. And what we do is we solve every single instance with every single solver, running with a time limit of 1,000 seconds here. And then we say, for example, at the 1 second mark, of all of the instances for a particular solver, so for example, for Glasgow, how many of those instances did we solve in 1 second or less? So I'm not saying how many instances can I solve in 1 second. I'm saying how many instances individually took 1 second or less to solve. I have seen a paper that has reported how many instances can we solve in 1 second, where they start on instance 1 and then instance 2 and then instance 3 and so on, and then stop when they reach an instance they can't solve. That's you can think about why this might not be a good way of reporting results. But what you're looking for in these plots is lines that go up and to the left. So solvers that can, on average, solve instances very, very quickly, and that can solve most problem instances. And if you look at this plot, okay, my solver is at the top, so I win a prize. The other interesting thing here is looking at the RI solver. So the purple line, you can see if you run RI with as a 1 millisecond time limit, it can solve over 8,000 of the problem instances, whereas my solver can't start itself up in a millisecond. This is kind of interesting. But if you look at this plot, okay, the top 2 solvers, Glasgow and Pathlad, these are both constraint programming solvers. The 2 solvers below are connectivity solvers. So you would conclude that, okay, constraint programming is the best way of solving these problems and move on. Yes? Right. So the question is, do these plots depend on the order of the instances? No. So what we're doing is we're running every single instance separately. And then you pick a timeout and you say, of the instances, how many of them successfully solved in under that amount of time? So it very specifically doesn't matter what order you run the instances in. And in fact, it could be the case that if you pick 2 solvers, for example, Glasgow and VF2, it could be that the set of instances that they are fast on doesn't really overlap. This isn't really the case in subgraph isomorphism, but for other problems this happens. Yeah. Yes.
So you think this is better than Cactus?
Yes.
Nice thing about Cactus is it tells you the total time, where this is not.
They tell you the same thing because you can flip the axes.
Cactus I've seen it's a total runtime plotted versus number of problems solved. Right? So as you solve more problems, you have to the plot time of that problem. So at any given point, you know the total time it took to solve. Whereas here, you just know the maybe this is a different difference.
Yeah,
It's about whether you're plotting total time, cumulative total time versus this is more like a histogram.
yeah. So you can read off the same thing if you want. Is it would be the integral of the curve, something like that? Yeah, you can read the same data off. The argument for using cumulative distribution functions, not cactus plots, so there are two arguments. One, the statistics literature consistently uses cumulative distribution functions. Like this is a thing that has a name where your favorite graph plotting software can actually plot these. Whereas for cactus plots, it is, okay, you sort the instances by runtime and then you plot them as a histogram. The other argument here is that you should have your dependent variable on the x-axis. So the x-axis is the thing that you can change. And in this case, you're allowed to vary runtime. You would pick a different choice of timeout, whereas you can't say, I'm going to alter the number of instances that I solve. Holger Hoos has very strong opinions on this topic. I think he is slowly converting the SAT community to his way of thinking. Yeah. Okay, so concluding that constraint programming is best. Except that this is not what a lot of papers say. A subset of these benchmarks are what's called the Mivia test suite. This is from a lab in Italy. The way they generate instances is as follows. They generate a random target graph according to certain properties. So they might decide they're going to create a sparse connected graph with a certain degree distribution. And then they take a random connected subgraph and call that the pattern graph, and then they permute the vertices in the pattern graph so it's not too easy to find it. So what you'll get here is these instances are always satisfiable if you generate them this way. It is always possible to find a pattern inside a target because you're starting off by creating a pattern that is a subgraph. And it turns out these instances are very, very easy to solve in practice for various reasons. And a lot of papers will only use these instances for benchmarking. And if you do this, well, you look at constraint programming and you say, these constraint programming solvers take over a millisecond to start running. This is terrible, whereas my solver can solve a problem in a tenth of a millisecond. And you will conclude that actually connectivity algorithms are the best approach. Now, you have to be a bit careful of this because in practice, people do not just want to solve easy, satisfiable instances. So draw your own conclusions there. Okay, so what is constraint programming? A constraint satisfaction problem has some variables. Each of these variables has a domain of possible values. And usually we think of these as integers. So I might tell you that x is between 1 and 10, y is between 1 and 3, and z is either 0 or 1. So this is like in Boolean satisfiability, except we are not limiting ourselves to Booleans. Our domains can be a finite subset of integers. And the problem is to give each variable a value from its domain whilst respecting all of the constraints. And here, constraints really can be anything that you can write down and describe or write an algorithm for. So a constraint might be that x plus y equals 5. It might be that x, y, and z are all different, and so on. So how do we express subgraph isomorphism as a constraint satisfaction problem? we're going to have a variable for every pattern vertex. So our pattern graph gives us the variables, and the domains are going to be the target graph vertices, which I'm going to think of as numbers. And the way I'm going to think about it is we're constructing a function or a mapping. So we are constructing a mapping that says, okay, send this pattern vertex here, send this pattern vertex here in the target graph, and so on. Okay, does this make sense to everyone? Okay, so what about the constraints? The first is we're looking for an injective mapping, so we're not allowed to map two different pattern vertices to the same place in the target. One way we could do this is we could say that, so variable A is not equal to variable B, variable A is not equal to variable C, variable A is not equal to variable D, and so on. And then B is not equal to C, B is not equal to D, C is not equal to D. This is what you would do if you were encoding this in satisfiability. In constraint programming, we like high-level constraints. And we will just say that variables A, B, C, and D have to be all different. And I will explain to you what we can do with this when we have this information. And then adjacency. So what do we do about edges, making sure that the pattern we're finding is actually what we're looking for? So if I have vertices A and B adjacent in the pattern graph, then I want to say that under the mapping, whatever I get is equal. So if A and B are adjacent in the pattern graph, then f of A and f of B have to be adjacent in the target graph. And one thing we could do is we could create a constraint for every edge in the pattern graph. So if these two vertices are adjacent, then you're only allowed to map to one of the following sets of options in the target graph. If you try and encode this in SAT, you end up with an encoding that has n to the 4 clauses, or if you're really clever, you can get this down to n to the 3 clauses. In practice, in constraint programming, we will write a special constraint propagator to do this instead, so we don't have to worry about an encoding being large. So for adjacency, we are just going to say, okay, I am going to give you an algorithm that will tell you what adjacency will mean, and we'll take it from there. Okay, we have some variables, we have some values. How do we solve the problem? And again, this may look familiar based upon yesterday's talks. I'm going to do a backtracking search. I'm going to pick a variable that has more than one value remaining, and I'm going to try each of its values in turn. So I'm going to pretend that this pattern vertex gets mapped to this target vertex, and then I'm going to see what the consequences of this decision are. So firstly, because of injectivity, nobody else can be mapped to this target vertex. So I'm going to eliminate the target vertex from every other domain. And then I'm going to say, okay, adjacency. Any variable that is adjacent to my chosen pattern vertex has to be mapped to something that is adjacent to my chosen target vertex. And I'm going to go through these values. And it could be that after we've done this, we are forced to map a different vertex also to one specific place. So it might be that if I map vertex A to vertex 1, then this forces vertex B to go to vertex 2, in which case we can learn some more and we can start propagating adjacency and so on in a loop. Okay, and we will keep running this until we can't infer anything else. This is like the unit propagation that we saw yesterday. Now at this point, there's a few things that could happen. One of our variables might have its domain wiped out completely. So we're saying there are no options left for where you could put this vertex, this pattern vertex. In this case, we've made a bad guess and we have to try something else. It might be that we're lucky and every single variable has exactly one value left in its domain. In this case, we've found a solution and we can stop. Or it might be that some of our variables still have multiple values left. In this case, okay, we're going to have to do a recursive call. We're going to have to pick another one of these variables and try each of its values in turn and so on. So we get a backtracking search tree. Is this clear? Does this make sense to everybody, the basic idea behind the algorithm? Do we ever restart? Yes, and I will talk about that this afternoon. Everything else that we're going to do is taking this algorithm and making it less simple. Okay. Okay, data structures. This is the big difference between subgraph solving and generic constraint programming solving. We need to store for every variable a set of possible values. And in this data structure, we need to be able to do a few things. We need to be able to test whether a specific value is present. We need to be able to remove values from a domain. And we need to be able to count how many values are left in a domain. And this data structure has to have some way of being copying or backtrackable or something. What data structure should we use? Suggestions? A stack? We could do a stack, the Sat solver trail data structure. A set of some kind, yes. Would be copying the entire set, but that's okay. Copying things is potentially cheap. A bit vector. Yes, the objectively correct answer is we are going to use a bit vector here. So what do? We have a big binary string. If I have, for example, 64 vertices in my target graph, I will have 64 bits. A bit means a bit takes a value 0 if a value is not in a domain, and 1 if a value is present in a domain. Why do we use a bit set? Well, a few reasons. First, it takes up very little memory. Even if we have, say, 1,000 vertices, okay, I can write out 1,000 bits. It turns out that all the operations we want to do have incredibly efficient operations on bit sets. We heard yesterday morning that you can do 10 to the 9 computations per second on a modern processor. If you're using bit sets, you can do about 10 to the 11 operations per second because you can work on more than one bit at the same time. So on modern processors, you can do operations on 512 bits or 1,024 bits in every clock cycle. So rather than doing one adjacency operation per clock cycle, I can do 1,024 adjacency operations per clock cycle. So this is why bit sets are great. Okay, let's start getting a bit clever. I am going to tell you that in no possible solution to this problem with a pattern on the left and a target graph on the right, could we map pattern vertex P to target vertex T. Now, why is this? The degree of a vertex is the number of neighbors, so the number of things next to it. If I have a pattern vertex that has 3 neighbors, I can never map this to a target vertex that has 2 neighbors, okay? Because all of my neighbors have to go to different points. And in general, if I have a pattern vertex of degree D, I will never be able to map it to a target vertex of degree less than D. So I can straight away at the top of search before doing anything, eliminate any value from a domain that corresponds to a pattern vertex being mapped to something with a smaller degree in the target. I just don't have to consider these possibilities at all. Here's something interesting. Suppose I have a pattern vertex that has degree 3, so 3 neighbors, and the degrees of my neighbors are 4, 3, and 2. Okay. Now I have a target vertex of 4 neighbors, so I'm allowed to map a pattern vertex of 3 neighbors to a target vertex of 4 neighbors. But suppose the target vertex neighbors have degree 4, 2, 2, and 2. Okay. I claim we can tell straight away this is never going to work. So my vertex in the pattern has neighbors of degree 4, 3, and 2. So I'm going to have to map my neighbor of degree 4 to somewhere in the target whose neighbor has degree 4. That's okay. But then I have my neighbor of degree 3, and the only things that are left are neighbors of degree 2, 2, and 2. So this isn't going to work. The general algorithm here is you write down the degrees of your neighbors, and you sort the list, and then you do a pairwise comparison, just item by item, and you say, okay, this has to be greater than or equal to that, this has to be greater than or equal to that. So we're not just looking at our neighbors, we're looking at the neighbors of our neighbors, in effect, and making sure that that will work. And you can extend this out so you can look at the neighbors of the neighbors of the neighbors and so on. It turns out in practice, this probably doesn't help you very much. But certainly looking at the degrees of your neighbors seems to be a very sensible thing to do. And again, this lets us eliminate a whole load more combinations before we start searching. In fact, this is one of the reasons that constraint programming solvers are slow. It's the first thing we do is we go and calculate the neighborhood degree sequence for every single vertex in the pattern and every single vertex in the target. And this takes a little bit of time, not very much time, but a little bit of time. And in that amount of time, a connectivity algorithm that just starts off blindly guessing might have already found a solution. So this is one of the places that the trade-off comes in. Here's another interesting thing we might be able to do. Suppose I do some filtering and a target vertex disappears from every single domain in the problem. So what I'm saying is vertex A cannot be mapped here, vertex B cannot be mapped here, vertex C cannot be mapped here, and so on. If this vertex has disappeared from every single domain, it's like it doesn't exist in the target graph at all. So we could delete this vertex completely. Now, when you delete a vertex, you are decreasing the degree of a bunch of other vertices. And it might be that once you've done this, this decreases the degree enough that you can say, aha, this vertex can never be mapped here after all, I've changed my mind. And it might be then that a second vertex disappears from the domain of every target graph and so on. And you can do this. It's quite tricky to implement this efficiently to be able to keep track because you don't want to recalculate everything from scratch every single time. And potentially this leads to more filtering. And in fact, we can even do this dynamically during search. So if I try allocating a pattern vertex to a target vertex, it might be that subject to this assignment, a different target vertex disappears from every domain. So I can do the whole neighborhood degree sequence calculation again from scratch, looking at just the subproblem that we're working on. Doing this is moderately expensive, though. And this is, when we're designing these algorithms, there is a big trade-off between being clever and being fast. So I told you that every now and again, Christine Solnon comes up with a really clever algorithm that beats my solver. Christine's solver does detect everything during search, and it will recalculate degrees and so on. My solver doesn't bother. I do this once at the top of search, and then I don't keep going. I have found that this trade-off is worth making. If I was a better programmer, I might be able to implement this fast enough to pay off in practice. I haven't been able to. I would say that for a constraint programming solver, my solver is fast and relatively stupid. Christine's solver is very, very clever, does a lot more thinking, but is slower to do it. It's difficult to say which is the best solution here. Okay, adjacency filtering. If I map a pattern vertex to a target vertex, the neighbors of my pattern vertex can only be mapped to neighbors of my target vertex. If we're storing our domains as bit sets, what we're doing here is an intersection operation. So I'm saying that a domain has to be intersected with the adjacency set for a vertex. You can think about this a bit. The reason we use bit sets is because adjacency filtering is a single AND operation, which we can do in hardware in a single clock cycle. So if you're using a bit set, literally you are just ANDing together two words in a machine. This means that propagating adjacency is incredibly fast. Injectivity filtering. Okay, yes. Yes. So, okay, so that, yes, so the difference between a bit set and a bit vector. A bit set is a very simple data structure. You're just saying this is present or this is not present. With bit vectors, I believe you quite often want to track whether something is definitely true, definitely false, or you don't know. So you have 3 states rather than 2. So in this case, I'm just tracking in the set, not in the set, and nothing else. So. Okay, injectivity filtering. Yes. Yes, so yes. So the question here is, do I also need an additional data structure that actually tracks where the pattern vertex has gone? So once I've decided, and yes, I also need to keep track of a mapping as I go. So in addition to all of my domain data structures, I have a couple of options. I can either represent assignments as just being domains that have exactly 1 value in them. And I just remember, okay, if something has exactly 1 value, it means it's assigned. Or I can keep a separate data structure that has the mapping. And in this case, yes, I keep a separate data structure because it's convenient to have. Yeah. Okay, injectivity. Here is a puzzle for you. Let's suppose I have the following 6 variables, and I have found out for some reason that A is either 1 or 2, B is either 2 or 3, C is either 1 or 3, and so on. And you have to give all of these variables different values. Can you tell me anything? It's impossible, yes. Why is it impossible?
Uh, uh, or it's 6.
Yeah, so the explanation is you have 6 variables, 6 values. But if you look, that 4 and 6 only appear in D and don't appear anywhere else, so this isn't going to work. This is not how a constraint programming person would answer the question, but I will explain this to you. Okay, matchings and all different. What I'm going to do, I'm going to create a graph out of my variables and my values. And I'm going to give you a really simple example here. I'm going to say that X is either 0 or 1, X1 is either 0 or 1, X2 is either 0 or 1, and X3 is either 0 or 1. And they have to take different values. Okay, so I'm asking you to color a triangle using 2 colors, which we saw yesterday that you can't do. Okay, and I claim you can detect this straight away that this isn't possible. What I'm going to do is I'm going to create this this value graph. I'm going to write my variables on the left-hand side and my values on the right-hand side, and I'm going to draw an edge from a variable to a value if that value is an option for that variable. Okay, now a maximum cardinality matching is where you pick as many edges as possible from a graph, but you're only allowed to use each vertex at most once. Okay. There is a polynomial time algorithm for this. It's based upon growing up a matching using what's called augmenting paths. This is a fairly easy algorithm. It's in most algorithms textbooks. What I claim, there is a matching which covers each variable, if and only if the constraint can be satisfied. So in this particular case, I find a maximum cardinality matching. Here is one option. I'm only covering 2 of the 3 variables, so there is no way of satisfying this constraint. Suppose that I said that X2 could also take the value 2. Then now, okay, we have a maximum cardinality matching that covers all 3 variables. Okay. And in fact, there is a one-to-one correspondence between perfect matchings, some matchings that cover everything on the left, and solutions to the problem. So if you give me a solution to the problem, this gives me a matching. And if you give me a matching, this gives me a solution to the problem. Okay. Does anybody do Sudoku puzzles? Why? You can get the computer to do them for you. It's so much easier. Okay. So a Sudoku, if you've not seen it, you're given some clues. You have to put the number 1 to 9 in each box. Every row has to, every value on a row has to be different. Every value on a column has to be different. And then for the 3 by 3 squares, everything in the box has to be different. How do humans solve Sudoku if they're good? Okay. What I have here is just one row from a Sudoku puzzle. And I'm going to say that the values in the boxes are that you've worked out that the first box is either 1 or 8. The second box is 2 or 3. The third box is 2 or 3. The fourth box is 2, 4, or 5, and so on. Can anybody tell me anything? First box has to be a 1. So what's the next one, sorry? In fact, 1, 2, 3, 4, 5, 6, 7, 8, 9 does work as a solution to this. There are reasons it might not work in others. Are there any other things you can tell me about values that might not occur? So here we have a 2 and a 3 and a 2 and a 3. So I don't know whether the second box is a 2 or a 3. I don't know whether the third box is a 2 or a 3. But I know that nothing else could possibly be a 2 or a 3. So none of those values in red can occur. Okay. Anything else? Remove 5 from the last one. Yes, so we also have a 4, 5, a 4, 5, 6, and a 4, 5, 6. So I don't know exactly where 4, 5, and 6 are going, but I know that they have to be used in those 3 boxes. So they can't be used anywhere else. In particular, they can't be used there. Is there anything else? Been a while since I wrote this example, so I've forgotten, but I think that's everything that we can do now. Yep. Okay. So in constraint programming, we like to talk about consistency for constraints. When I say generalized arc consistent, here's what I mean. Pick a constraint, and then pick any variable in that constraint and give it any single one of its values. If the constraint is generalized arc consistent, then I can find a way of assigning a value to the remaining variables in the constraint such that that constraint is satisfied. Equivalently, what I mean is that every single value left in the constraint appears in at least one solution to that constraint. Possibly not other constraints. There might be other constraints that mean this doesn't work. What I'm saying is if you look at one particular constraint, then everything left in the domains occurs in at least one solution. Okay. Now we need to talk about whole sets. So if I have a set of n variables from an all different constraint where I have exactly n values between all of those different variables, we call this a whole set. And I can delete those values from every other variable in the constraint. There is a classic result in combinatorics. If we can find every single whole set and delete all of those values from the remaining variables in the constraints, then this is the same as deleting every edge from the matching graph which cannot appear in a perfect matching. So what we're saying here is, if we can find and delete every single whole set, we delete every value that doesn't appear in at least one solution to the constraint. So this is the same as generalized arc consistency. Okay. Now here's the problem. We have 2 to the n potential whole sets. So considering them, yeah, we can't really consider all 2 to the n sets This wouldn't be fast enough. And it turns out that just enumerating every single perfect matching is NumPy hard. If you've not heard NumPy, this is kind of the equivalent of NP complete, but for counting problems. So probably not something that we want to do. But it turns out there is a polynomial algorithm that will identify every single deletable edge. I will not go over the algorithm in detail, but I do have an animation because I taught this in an undergraduate class once. So I spent quite a lot of time drawing this picture. I want to use it at every opportunity. What do? We're going to write all our variables on the left-hand side. We're going to write all our values on the right-hand side. And we are going to draw an edge from a variable to a value if that value is present in that variable's domain. Okay. Now I'm going to find a maximum cardinality matching. This is a polynomial time algorithm. It doesn't matter which one I find, I just need to find one. Okay. Now I am going to put some directions on my edges. So anything that is present in the matching, I'm going to make into a line going from right to left. Anything that is not present in the matching, I'm going to have an arrow going from left to right instead. Okay. Next thing I'm going to do is find the strongly connected components in this graph. So a strongly connected component is a subset of vertices where you can walk from any vertex in this subset to anything else in this subset. So if you have a directed graph, you can always partition this into strongly connected components. This is Tarjan's algorithm, which is, I think, one of the nicest algorithms ever designed. It's very elegant. In this particular case, we get the partition as follows. It's just a coincidence or a carefully constructed example, but everything is next to each other on the picture. In general, your components could be all over the place, but I've carefully written this example so that I can draw my blocks so that everything is next to each other. Okay, what am I going to do next? I'm going to ignore every edge that occurs inside a particular component, and I'm only going to look at the edges that start in one component and end in a different component. And here's what we have. We have some edges going from right to left and some edges going from left to right. Edges going from right to left correspond precisely to assignments that are forced in the original problem. And edges going from left to right correspond exactly to all of the things that we said we should delete when we were doing this example by hand. This is either magic or it's a really neat algorithm. Take your pick. I'm not going to prove to you why this works in general. If you understand augmenting paths and maximum cardinality matchings, and you sit and stare at this for half an hour, you'll understand why it works. It is very nice to look at, though, if you have spare time. Okay. So we can do this. We're dealing with a problem where we have an all different constraint over all of our variables. We could run this all different propagator all of the time. It turns out that although this is a polynomial time algorithm, it's kind of cubic in complexity. Getting this algorithm to run really fast in practice is difficult. We heard yesterday that for SMT, you want your theories to be incremental, for example, so they don't have to recalculate everything from scratch. You want them to run very quickly. It's the same here. If you look around, there is a 60-page paper on how to implement the all different algorithm quickly, but it took the St. Andrews team 2 years to write. The difference between an optimized implementation of an all different algorithm and a slow implementation is about a factor of 1,000. So for all of those complexity theory people who tell you, okay, 1,000 is a constant factor, we don't care about constant factors. If the constant factor is 1,000, I'd say we care about it. We could also do all different on edges rather than vertices. This is even more expensive. This is another difference between my solver and Christine Solnon's solver. Christine solver does a lot of very clever all different reasoning. I do some cheap and quick all different reasoning that usually gets you most of the same results. Okay, distance filtering. I've told you that adjacent vertices must be mapped to adjacent vertices. you can work out, this is a theorem you can prove, vertices that are distance 2 apart in the pattern graph must be mapped to target vertices that are within distance 2 of each other. So vertices A and D in my pattern are distance 2 apart. We could not simultaneously map A to 1 and D to 4 because 1 and 4 are not within distance 2 of each other of the target graph. Okay. Similarly, if you have two vertices that are within distance k of each other, they have to be mapped to vertices that are within distance k of each other. The question is how we turn this into something useful that we can put inside an algorithm in practice. This is where things get fun. Okay. I am going to take a graph, G, and I'm going to define a new graph for you, G to the power D. What I'm going to do, I'm going to take the same set of vertices. Now, suppose in the original graph, we have two vertices, V and W, and the distance between them is at most D. Then I'm going to put an edge between these vertices in G to the power D. So what I'm doing is I'm taking a graph, and I am adding in edges for anything that is distance 2 apart. Okay. And here is something else you can prove. If I give you a subgraph isomorphism from a pattern graph to a target graph, this will always also be a subgraph isomorphism from the pattern graph raised to the power D to the target graph raised to the power D for any choice of D that you pick. So if you're finding a subgraph isomorphism from a pattern to a target, you're also finding a subgraph isomorphism from the pattern graph squared to the target graph squared, and so on. But why is this helpful? Anything I can tell you about subgraph isomorphism, I can also apply to subgraph isomorphism on the squared graph or the cubed graph, and so on. For example, I can reason about the degrees of vertices in the square graph. I can reason about neighborhood degree sequences in the square graph. And when I do adjacency filtering, if I propagate adjacency on the original graph and on the square graph, I am propagating distance 2 filtering effectively for free. So when we're designing a subgraph isomorphism solver, what we do is we design a solver that doesn't just find a mapping from a pattern graph to a target graph. It finds something that is simultaneously a mapping from a pattern graph to a target graph and from the pattern graph squared to the target graph squared, possibly from a pattern graph cubed to the target graph cubed, and so on. And in fact, we can do something stronger than this. Rather than saying what is the distance, we can say, is there a simple path of length exactly 2 between two vertices? So you're not allowed to repeat a vertex. So we're not saying, is the distance 2? We're saying, does there exist a path of length exactly 2 between these vertices? And now we can define a graph G to the power exactly 2, where I make vertices adjacent if and only if there is a path of exactly length 2 between those vertices. And again, you can prove any subgraph isomorphism from a pattern graph to a target graph is also a subgraph isomorphism from pattern to the exactly 2 to target to the exactly 2. And we can do other things. For example, suppose I can create a graph where we look at whether or not there are exactly 3 paths of length 2 that don't share any vertices between two vertices in the original graph. And again, I can solve a subgraph isomorphism problem on the original problem, plus on this G to the power 2 paths of exactly length 3. And we can construct these graph pairs once at the top of search, and we can create as many really of these graph pairs as we want, and we can solve a subgraph isomorphism between every pair in these graphs simultaneously. And the advantage here is we get lots and lots of extra constraints that tell us straight away you can't map this vertex here. If you map this vertex here, you can only map this vertex here, and so on. And this really, really cuts down the search space. To give you one more example, looking at the pattern graph on the left and the target graph on the right on the top, it's not immediately obvious whether or not, yes? Yeah. So in what we can say is, are there exactly, if we have, are there at least 3 paths of length exactly 2? Then this pair of vertices has to be mapped to something that has at least 3 paths of length exactly 2. You can have additional paths. This example probably explains why this is useful. Pattern graph on the top left to the target graph on the top right. Not immediately obvious that there is no solution. I'm going to create these graphs p to the 1 plus 2 now. So I'm going to have vertices adjacent in p to the 1 plus 2 if there is a path of length exactly 1 and a path of length exactly 2 between these 2 vertices. Okay. And I can do the same for the target graph. And you see immediately the pattern graph on the left has this big component with 4 vertices and lots of high degree vertices, and the target graph doesn't. So straight away, I can tell you just by constructing these p to the power 1 plus 2 graphs that there is no solution to this original problem, and it becomes obvious. So no backtracking search whatsoever. And yep. Yes, so 1 plus 2, I have an edge between vertices A and B in 1 plus 2. If there is a path of length exactly 1 between A and B in the original graph, and there is a path of length exactly 2 between A and B in the original graph. Okay. And in general, we can do this for arbitrary different shapes. You can pick all sorts of crazy things. Like is there a triangle and a path of length 4 between these 2 vertices? Any shape you want, you can create these graph pairs. Yes. From A to E of length 2, but there is not a path from A to E of length 1. So it's an and operation. So there has to be both a 1 and a 2. Yeah. So this and operation is why it's so powerful. So one of the tricks here is to pick, we could do this for a million different graphs, a million different shapes, but then it would be very expensive. We'd have to compute these graph pairs for a million different shapes and propagate it. So the trick here is to pick a small number of really good shapes for any particular graph and use just those shapes during search. And if you can do this, there's an example in the upcoming chapter in Don Knuth's The Art of Computer Programming, where he has these crazy complicated graphs and saying, is there a subgraph isomorphism between them? And these are graphs that are hard to solve for existing solvers. And he has identified a particular shape graph that cuts this one specific problem instance down to a very easy problem. In general, we don't know a way of identifying good shape graphs to use on an instance by instance basis. So I have a hard-coded list of good shapes that seem to be quite good in practice. This is an open problem as to how to identify shapes. Yes. Yeah, so a shape could be 1 plus 2, or it could be 3 edges of length 2. It can be anything that you want. Yeah. Yes. Has somebody tried to apply machine learning? I did an algorithms portfolio paper a long time ago with Lars Kotov. Annoyingly, machine learning is quite good at picking which shape graphs you use, but it does it by cheating. Machine learning gets the right answers, but in a way that completely doesn't generalize beyond the training data. It passes all these, tenfold statistical cross-validation checks, and it still completely doesn't work when you give it a graph that it hasn't seen before. So, yeah. Good one to work on if anybody's looking for a challenge. Okay. Remember I told you about induced isomorphisms. So this is where you're not allowed to have extra edges. What you can do is take a graph and define its complement. So the complement of a graph, there is an edge present, if and only if there is not an edge present in the original graph. So if I want to find an induced isomorphism, all I have to do is find something that is simultaneously a non-induced isomorphism and a non-induced isomorphism between the complement graphs. And in particular, this means that I can reason about, for example, the complement degree of vertices. So if I have something that is not connected to 5 neighbors, I have to map it to something that is not connected to 5 neighbors in the target graph. And we get all these theorems for free just by saying, okay, I'm not going to care about solving induced. I'm going to solve non-induced simultaneously on the original graph and the complement graph. If you remember, I mentioned partially defined graphs where I said there are some edges present and some edges not present and some edges you don't know. There is a way of expressing this as a pair of homomorphisms. So you can express the edges that are exactly present in one graph and not present in another graph. I will leave it to you to work out how you do this because I get very confused every time I try and do it, but it is possible. Here is a final, completely crazy idea. If a pattern vertex is contained in a k-vertex clique, it must be mapped to a target vertex that is contained in at least a k-vertex clique. So here's an example. The 3 vertices that I've shaded in red all appear in a 3 clique. The 3 vertices I've shaded in red do not appear in a 3 clique. So I cannot map any of those 3 vertices on the left to any of those 3 vertices on the right. Now, clique finding is NP complete, NP hard. Am I seriously claiming that we run an NP hard solving algorithm on every single vertex in the pattern graph and every single vertex in the target graph before we start running the solver? Actually, yeah. It turns out that although clique is NP hard, clique is so very easy to solve in practice that quite often this pays off. This lets you cut down enough vertices that it is worth doing. In particular, this is valid even if you are looking for non-injective isomorphisms, so homomorphisms. Basically, everything I've told you so far only works because of injectivity. The injectivity is a really powerful property for coming up with invariants. This is just about the only rule we have that works even when you don't have to have injectivity. So this is potentially where it's useful. So in the pattern graph, we go over every vertex in turn. We say, find me the biggest clique containing this vertex and looking at its neighborhood. So we get an exact solution for every pattern vertex. We speed this up. If I've already found this red clique, for example, looking at the second vertex, I can hot start the clique solver saying, okay, I know that this vertex on the left is present in at least a 3 clique, find me something bigger. So that speeds things up a lot. If we've found a clique for one vertex, we can use it to hot start the clique solving for some of the surrounding vertices. Then for the target graph, we also solve the maximum clique problem, except we tell it, so suppose the biggest clique I found in the pattern graph has 6 vertices. We don't actually care whether or not the maximum clique is 7 or 8 or 9 or 10. We just say, decide whether there is a clique of at least 6. So we run the solver in a restricted mode saying, okay, find me the maximum clique, but if it's bigger than 6, then you can stop.
So for soundness, you require in the target graph that it should be able to tell that there is no clique.
Yes.
Okay.
Yes. So for soundness, so if we underestimated in the pattern graph, it wouldn't cause a problem. If we underestimate in the target graph, it's bad. Yeah. Yes. So how does this help? Sorry.
When you don't have injectivity, can't
Yes.
you just map all the vertices in a clique to one vertex?
Okay. So when you don't have injectivity, the rule is adjacent vertices have to be mapped to adjacent vertices. So everything in and a vertex typically is not adjacent to itself unless you have a loop.
Oh, you don't have loops on this.
So everything I'm telling you today is pretending that loops don't exist. Yes. So if you have loops, you can't do this. But then the homomorphism problem, if you have loops, is easy because you just map everything onto the vertex that has a loop. So, okay. Okay, search. Let's see how we're doing for time. Okay. So I'm telling you, we're going to do a backtracking search, and we're going to pick a variable to branch on. So pick a pattern vertex, and we're going to try giving it each of its remaining values in turn. The way you pick which pattern vertex to branch on is absolutely vital for performance. One of the reasons that constraint programming works in practice is because we have all sorts of heuristics that tell us if you are going to branch, you should do the following. And in constraint programming, whenever we branch, we know it's a good idea to branch on variables that have smallest domain first. So if I have a variable A that has 2 options left and a variable B that has 20 options left, I should branch on variable A before branching on variable B. The other general rule we have in constraint programming is you want to branch on variables that are involved in a lot of constraints. The idea is that after you make a decision, it's going to give you a lot more information that helps you decide if you've made a bad guess, you'll detect this as quickly as possible. The general principle here is if we've made a mistake, we want to identify it as quickly as we can. So for subgraph isomorphism, I claim what you want to do is pick the smallest domain first, and when you're tie-breaking, you tie-break on highest degree. And interestingly, this will nearly always pick a vertex adjacent to something that you've already branched upon, because after you've assigned a vertex, it really cuts down the options for the neighbors of that vertex. So this is in fact similar to the connectivity rule that is being used in the non-constraint programming solvers, except it's a bit more powerful. And again, I'll show you examples of why it's more powerful later on. Now, value ordering for target vertices. So I've decided I am picking this vertex. Where am I going to map it? I claim it's a good idea to try to map a vertex to a target vertex with as many neighbors as possible. The hand-wavy intuition for this is you're picking a vertex and you want to leave as many options as possible available for your neighbors. So picking a vertex of high degree will do this. Okay. Let's just do a quick sanity check on this. And I am just looking at value ordering heuristics here. So which target vertex do we do? And I am only looking at satisfiable instances from the benchmark set. So solutions where there is actually a solution. And I'm going to show you 3 options. I'm going to show you degree, which is what I claim, okay, we pick a vertex of highest target degree. Random, so we branch completely randomly. And anti, where we pick vertex of lowest degree first. And looking at this plot, this confirms what I said. So the degree line is the best. It is highest up and furthest to the left. And if you measure the horizontal distance between the lines, you can see that tells you kind of how many times faster one option is than another. It's not exactly. The set of instances might be different, but approximately it tells you how many times faster one algorithm is than another. We see this is a log scale. So anti-degree is maybe 50 times faster than picking degree. For variable ordering heuristics, the difference is even bigger. And then doing just as a sanity check, looking at instances that have no solutions. So in this case, we would have to explore every possible combination of every value anyway. So it doesn't matter what order we explore them in, at least for a simple backtracking algorithm. And we can see, yes, fortunately, this is the case. Okay. I think I am going to put this slide up. Sorry, Khalid.
Why do you have so many? I mean, this is a bit about benchmarks, but you have like overwhelmingly many unset instances.
Yes.
Is that what people care about?
why do we have so many unsat instances? It is to do with so a lot of the application data sets, what they'll have is they'll have a set of pattern graphs and a set of target graphs. And a pattern will appear in 1 or 2 or 3 of the targets and not the rest of them. And we're running all pairs in the benchmark instance. So this is kind of fairly realistic from an application perspective, that if you're doing like chemical filtering, you know, this fragment might be present in these 10 molecules, this fragment might be present in these 10 molecules, and then all the rest of the database, they're not present. So that's where that bias comes from. Okay. I will put this slide up before lunch, and then after lunch, I will make this much more complicated. We saw this graph yesterday, except it didn't say clique, it said graph coloring. What I am going to do here is take a 150 vertex pattern graph, and I'm going to vary the probability of any 2 edges being present, going from 0 to 1. Okay. And what I'm going to do is I'm going to look at what proportion of the instances that I generate are satisfiable. So this is this green box. And what you can see is as I increase the number of edges, I'm going to say, does this graph contain a clique of 20 vertices or not? If I give you a graph with no edges at all, it's not going to contain a 20 vertex clique. If I give you a graph where every edge exists with probability 1, then yes, it's going to contain a 20 vertex clique. This is the green blob here. And what you can see is there is this very sharp phase transition from where no, there is not a 20 vertex clique to yes, there is always a 20 vertex clique. And there's only a very, very narrow range of probabilities where some of the instances we generate have a 20 vertex clique and some of the instances we generate don't. And then the purple line is how hard are these instances to solve using a clique solver. And what you can see is we have this peak that, this is on a log scale, so this is a very, very pronounced peak. We have this complexity peak that right around where the instances are almost satisfiable or half of them are satisfiable, these instances are by far the hardest for clique solving. Okay. I'm going to explain after lunch how this generalizes to subgraph isomorphism when we're not talking about cliques, and why this justifies branching on smallest domain first and branching on patterns, and how we can use this information to design better algorithms. But I think I will stop for lunch now, unless there are questions. Yes. Oh.
Yeah, so I have a set of questions. One is, so this property of a graph containing a clique of 20 vertices.
Yep.
I'm just wondering whether this can be read from this graph, but this property is expressible in first order logic. You just say that there
yes.
is this x1 to x20 says that pairwise there's an
Yep.
F between. And it is also known that first order logic has the 0-1 law, which means that every first order expressible property in the limit is either almost surely true or almost surely false.
Yep.
Which means either every graph satisfies the property or no graph satisfies the property. Now, clique, presumably, I'm not sure whether it is almost surely true or false, but given this, and this is true for Gn 1/2 Gn for any p, which is a constant. In fact, there's a very interesting result where p can be non-constant as well. But can we read from this plot? I mean, for example, you have the edge probability is 0.2, but it's not the case that you are looking at graphs with a certain number of vertices, is it?
So from the title, this is graphs of 150 vertices.
Oh, okay.
Yes. So if you had infinitely many vertices, then this doesn't work. But we're looking specifically at a graph of a fixed number of vertices and then varying the edge probability.
Right.
Yeah.
Okay. So presumably, yeah, I mean, using this property, maybe you can infer something about this when you take it to make 150, which is to a very large number. Maybe
Yes.
something can be
Oh.
inferred from the fact that you will get, probably every graph will either satisfy this property or not. You can probably lift this picture to an n vertex graph.
Yes,
last
so we can in fact tell you exactly where this complexity peak or where this shift from unsat to satisfiable occurs. Yeah. There's a fairly simple formula. Proving that the formula is sound is the tricky bit. Yeah.
Right. Okay, that was one question. The other question was, so if you, trying to see for extensions of the same method that you have. One is you're looking at subgraph, which is an injective homomorphism.
Yep.
Now, you could drop the injective tree and you can
Yes.
just ask for a general CSP. So do these methods, of course, the difficulty there would be that because this is injective, once you have fixed a vertex, you have mapped a certain pattern vertex to a certain target vertex, you know that no other vertex can take on this particular value.
Yep.
Whereas, of course, when you have general CSPs, then the possibility becomes alive again.
Yep.
But what happens if you were to consider graphs, pattern graphs that are complements of bounded degree graphs? Okay, so that means
Yeah.
there are only finitely many what do you say? Bounded degree would mean it's just fixed number of things as neighbors,
Yep.
and the complement of that would mean that there are high number of neighbors, but only finitely many things which are. So, will the same method? How will this method work if you had pattern graphs? The method that you have work for pattern graphs that are of this form.
Let's see. I suspect that degree reasoning wouldn't do particularly much in this case. It would depend on what your target graph looks like as well. We're always, the question is never what does the pattern graph look like? The question is always, does the pattern graph have some features that let you, is there some interesting structural information in the pattern graph that only occurs in certain places in the target graph that let you narrow the problem down? So for example, if you give me a k-regular pattern graph and a k-regular target graph, this is an annoying problem because somehow the structure is the same in the pattern of a target, so I can't do any reasoning about it. If you tell me that something is adjacent to all but a small number of vertices, my gut feeling is that it will be really hard to get any filtering out of this in general. And you might have to start looking for other properties that maybe distance reasoning tells you something or clique reasoning tells you something. Yeah, in particular, I think if you start taking CSPs and then doing homomorphism finding problems, this is not necessarily going to get you a good solver for a problem, because you're taking a problem and you're encoding it into a slightly different CSP, and you're probably losing information and making a problem bigger when you do this. So I don't think that gives you a helpful algorithm.
And one final thing, this fact about taking these powers, right? That's a very nice idea that after all, this it must if there's a homomorphism, if G is a subgraph of H, then G to the power D would be a subgraph of H to the power D. Now I was just wondering if we the same thing about taking powers. There's this notion of a topological minor, which is that there's a path between, instead of there being, if two vertices, instead of being an edge going to an edge, you can make an edge go to a simple path, an induced path, in fact.
Yeah.
Now you could do something similar if you want to generalize this problem to finding whether G is a topological minor of H, which is just about enlarging a path, which is subdividing a path into a long, subdividing an edge into a long path. Is it possible that the same methods work? Because probably all that needs to be done is first in the target graph, you take its power to the n, maybe.
Yeah.
You just find out with respect to this kind of path thing. If there's a path from G to vertex 1 to vertex 2 of some length n, then you have all of these individual edges coming in. will this, can this algorithm be used to also find whether, generalized for this
Find
setting?
minus. Okay, so the fully general proof of that the shape graph reasoning works is simply that if you compose homomorphisms, you get a homomorphism, or if you compose subgraph isomorphisms, you get a subgraph isomorphism. So if finding minors composes, then this works.
Yes.
Yeah. So if a minor of a minor is a minor,
Yes, it is.
then this will work.
Then
Yeah.
this will work. Yes. And
That's all you need for the proof.
then
So yeah.
that's great.
Any further questions?
Chemistry application, right? So
Yeah.
the graph only tracks the adjacencies. It doesn't capture the orientation
Right.
fully.
So in chemistry, yes, people also care about this that 3D information about what the shape of a molecule actually is. The basic subgraph finding problem does not track this information in any way. You can apply various labeling constraints to start tracking this information with varying degrees of success. As I understand it, even calculating what the angles are in a real molecule can be quite a complicated problem. And if you're looking for molecular fragments, I believe what can happen is you can have some things that do not have bonds between them, but that are still spatially close, that you can take away and decompose the molecule that way. So the biochemistry applications where they care about this sort of thing, adjacency does not represent a chemical bond so much as it represents some kind of physical adjacency or some kind of electrical property that I don't understand. So it's not necessarily the case that we're just saying, okay, atoms are vertices and bonds are edges. There are more complicated encodings for real world problems.
So each adjacency graph is essentially representing all possible orientations with the same adjacency. It's kind of an abstraction or
Yeah, so a graph is a model of a molecule. It's not a perfect description of what a molecule is. If you find cases where the model is bad, so this is a constraint programming approach. You can add constraints to the problem. So if you really understand the data you're working with, then you could say, okay, if you map this vertex to this vertex, then you have to do something involving the angle between vertices over here. You can add these in as additional constraints to the problem if you know enough about the problem you're solving.
okay.
Okay, so I guess let's conclude this session. So lunch is going to be where it was yesterday, and we will resume at 2 o'clock.
Thank you.
Okay, so let's get started again. Ran?
Yep. So just to recap where we were talking about doing a backtracking search, and I had made the claim that it's really important you decide which vertex to branch on and where to send it to. And I had suggested, okay, for variable ordering, so which pattern vertex do we branch on? We want to pick small domains, so things that only have a few options left if we can. And we want to assign to the highest degree tiebreak on highest degree vertices. And then when we're assigning, we want to pick vertices adjacent to things that we've already picked. And for value ordering, I say we want to go from highest degree to lowest. And we had seen some results. We'd seen for satisfiable instances, if we branch assigning to high degree vertices first, we get an algorithm which is much better than random branching or assigning to low degree vertices first. And on unsatisfiable instances, this did not make a difference, but variable ordering heuristics do still matter for unsatisfiable instances. And we had got as far as this graph, which is the same as a graph we saw on the first day, except for a completely different problem. We see if we are looking at random graphs of 150 vertices and different edge probabilities, then, and we're looking for a clique of 20 vertices, what happens as we vary the edge probability? If we have no edges at all, we definitely don't have a clique. If we have all the edges, we definitely have a clique. And there is this very sharp threshold somewhere around 70%, 75%, where we go from being never satisfiable to always satisfiable. And this is where the hardest to solve instances are as well. Okay, let's try something a bit more complicated. We're going to decide now, instead of finding a clique, we're going to find a randomly generated pattern graph. We're going to fix the number of vertices in the pattern graph and the density. We're going to fix the target graph number of vertices and density and generate instances at random independently and see what happens. So here's an example. We have a pattern of 20 vertices and a target of 150 vertices. And now, instead of being a clique, the pattern density is going to vary, and we're going to fix the target density at 0.4. So if we have no edges at all in the pattern, we're looking for a non-induced isomorphism, so this is always going to work. So on the left-hand side of a plot, we are always satisfiable. On the right-hand side of a plot, we're looking for a clique in a fairly sparse graph. So this is never going to be satisfiable. And somewhere in this, somewhere in the middle, somewhere around 0.5, there is this threshold where we switch from being satisfiable to unsatisfiable. And again, if we plot the amount of search effort required to solve a problem, we see we're on a log scale here, so we see this complexity peak right around the area where we switch from being satisfiable to unsatisfiable. Okay. Now let's move to varying all the parameters. So in these plots, I am going to fix the size of the pattern graph, so the number of vertices in the pattern and the number of vertices in the target. And I'm going to vary on the x-axis the edge probability for the pattern, and the y-axis the edge probability for the target. In this top plot, the dark region, the red region, are unsatisfiable instances. The green region are satisfiable instances. And the very narrow region of white dots in the middle are where we get a mix of satisfiable and unsatisfiable instances. And again, you see there is this sharp transition. There is only a very narrow region where we get this mix of satisfiable and unsatisfiable instances. On the bottom plot, I'm using the same axes, but I'm plotting the difficulty for my solver to solve these problems. And darker colors mean exponentially harder. And again, what we're seeing is if we're near this phase transition, the instances are hard for the solver, but in the rest of the parameter space, the instances tend to be very easy to solve in practice. Okay. The white strip at the bottom are instances solved without search. So I would view lighter colors on here as being easier, and white instances as being so incredibly easy they're right at the bottom of the scale. Okay, and what about Christine Solnon's solver, LAD? Same thing, but plotting the difficulty of her solver. And again, you see, broadly speaking, our two solvers agree on which instances are hard and which instances are difficult. On these kinds of graphs, my solver is slightly faster than hers, but there's not a huge amount in it. Now looking at one of the connectivity algorithms, VF2, roughly the same thing, but there is a much, much larger hard region for connectivity algorithms and constraint programming algorithms. So we're seeing that constraint programming is doing better on hard instances. Okay. Can we get anything interesting out of these graphs? So we're going to pretend that every problem we ever solve is a random graph problem, which is a very dodgy assumption to make, and we shouldn't be doing this, but we'll do it anyway. What we want to do when we are searching, possibly, is to maximize the expected number of solutions in the subproblem that we're looking at. This is a general suggestion of how to design constraint programming search strategies. And we can calculate, I'll not go over this in detail, but we can calculate, if we assume that our inputs are random graphs, we can calculate the expected number of solutions to the problem based upon the target probability, target number of vertices, the target edge probability, and for the same for the pattern. And in fact, those predictions, I don't know how well this is showing up on those slides, but there is a black line on the top three plots which shows what that formula predicts, which fairly closely agrees with the data, except at the extreme ends. So this hand-wavy formula is fairly reasonable in practice. Okay, the argument for our branching heuristics. Remember, we want to branch on smallest domain first. Smallest domain first keeps the remaining domain sizes quite large. Which is kind of this left-hand bit, the injective mapping part of the problem. high pattern degree makes the remaining subgraph sparser. So I'm taking out a high degree vertex. This makes my remaining pattern sparser. So what's left, which again you can see is doing what we want on the right. And high target degree leaves as many vertices available for future use, which makes the U bit larger on the right hand side. This is all very dodgy and is making a lot of hand-wavy assumptions about random graphs and what we're doing, but it does give some rough justification for where heuristics come from. Okay, what if we're looking at induced? Yes. So number of edges. So in a non-induced isomorphism, you're going to have, how does this work? You have P choose two potential edges, and each one exists with probability Q. So then the chances of all of them mapping to something that exists in the target is U raised to that power. So this is kind of saying for every edge that actually exists, what's the probability that it's going to be there in the target? Yeah, induced, we can do a similar thing. We end up with this very interesting shape. We don't have a single phase transition. We're going from unsatisfiable to satisfiable to unsatisfiable, or depending upon the relative sizes of the pattern and target vertices, we might not have this satisfiable region in the middle. The interesting thing here is if we look at the difficulty, now we're seeing very hard instances around where the phase transition is, but you see this region in the middle is quite a dark color. We're seeing instances that are a long way away from the phase transition, but are still hard to solve. And this kind of goes against what a lot of papers have said in the past we should expect to see. But somehow we're deep inside a region that we know is unsatisfiable, but somehow my solver is still finding these instances to be difficult. So what's going on here? Is it just that my solver is bad at these particular kinds of instances? So we can do the same thing with Christine's solver, which is a CP solver, and you see the same thing. There are a lot of very hard instances in this middle region that can't be solved. So maybe constraint programming is bad. Let's try a connectivity algorithm. No. These instances are hard for connectivity algorithms as well. But maybe this is down to how we are solving the problem. Yeah, VF3 is another connectivity algorithm. Its behavior is a bit peculiar. I don't really understand why it finds things hard and why it finds. See those black dots down at the bottom? There are some very, very easy instances that VF3 finds ridiculously hard. This is interesting. I believe VF3 was overfitted to a certain benchmark set, and this is why it's so bad on every other instance. Okay, let's take a SAT solver. Yes. Let's see. Oh yes. So, okay, yeah, those should be easy unsat instances. Yeah.
Which remains much more close to the open source style.
Yeah. Yeah, no, somehow these are trivially unsatisfiable instances, but it's still finding hard to show. Oh, yeah. Okay, so what if we're all wrong? We should take a SAT solver and use these to solve a problem. So I'm looking at smaller graphs here. There are practical difficulties of using SAT to solve large target instances, but we get the same thing even on smaller graphs. And I've tried this with a whole bunch of SAT solvers. This middle region is also hard for SAT solvers. Yeah. Okay, but maybe this is down to how we're encoding the problem. You know, maybe we don't have a good SAT encoding. What about pseudoboolean solvers? Nope, they also struggle. Okay, the intuitive argument is possibly our solvers are bad about reasoning about adjacency and non-adjacency at the same time. that intuitively, if you want to solve these instances in the middle, maybe you have to be able to reason about adjacency and non-adjacency simultaneously. There is a reduction from subgraph isomorphism to clique finding that completely removes this adjacency, non-adjacency thing. The encoding talks entirely about compatibility rather than adjacency. I can put these instances into a clique solver, solving a problem in a completely different way. And it's still finding these middle instances difficult. So maybe there is something interesting and algorithm independent going on. It finds a maximum clique or clique decision, as you prefer. The reduction is you take the two graphs and you construct kind of a product graph, and then a clique in the product graph corresponds to an assignment in the original graph. I'd need probably half an hour to draw the reduction out and convince you it's right. But somehow it doesn't talk about adjacency or non-adjacency at all. It talks about the compatibility of pairs of mappings, which, yeah. I also tried an integer programming solver. I mean, integer programming solvers are very bad at subgraph problems, but yeah, also seems to be hard for integer programming. So there was a paper by Toby Walsh et al. From the 90s. That talks about something they call constrainedness. And they argue that what you should actually be looking at is this magic number, which is defined as 1 minus the log of the expected number of solutions over the log of the size of the search space, and that you should be trying to make this number not equal to 1. The argument here is that if this number is 1, then you're in an area of the search space where there are exactly the right amount of constraints, but you don't know whether this is satisfiable or not satisfiable. And if you move away from this area, either you obviously have no solutions, or you obviously have lots of solutions, and in either way it should be easy. And we can plot constrainedness. I'll not go into details, but roughly speaking, the dark region here, dark colors correspond to the most constrained region of the search space. And somewhat surprisingly, this more or less accurately reflects exactly what the solver finds. This, I think, is interesting because previously constrainedness had always been seen as being a slight refinement over expected number of solutions. Whereas here we have instances where constrainedness and expected number of solutions tell you very different things, and constrainedness is an accurate predictor of what actually happens in practice. But see, the take-home message for this is there is a principled way of designing these search heuristics if you make certain assumptions, and I'm not just magicking up smallest domain first and highest degree from nowhere. Although it would probably have been easier to try out a bunch of heuristics and see which one works rather than trying to derive this from scratch. Okay, one slight variation of the problem. Labeled subgraph isomorphism. So my vertices are going to have labels, and the isomorphism has to preserve labels. So carbon has to map to carbon, hydrogen has to map to hydrogen, and so on. As a constraint programming person, I think this makes the problem easier because you're telling me that the domain of this variable, you can straight away you can eliminate any infeasible label at the top of search. So if I have a carbon vertex in my pattern, I can throw out all the hydrogens and the nitrogens and so on. So I end up shrinking my domains down an awful lot. Okay. So let's do some experiments with randomly labeled graphs. Same idea, looking at different edge probabilities. And as I move from left to right, I'm increasing the number of different labels that I use. And you can see we get the same shape roughly, except when we have a large number of labels, do you see we have everywhere inside the satisfiable region, we have a mix of satisfiable and unsatisfiable instances. What's happening here is if you have, for example, a 20 vertex pattern, and you're using a lot of labels, it might be you generate some labels that don't occur at all in the target graph. So these instances are really obviously unsatisfiable. If I'm telling you have to map carbon to carbon, if my pattern graph has a carbon vertex and my target graph doesn't have any, then these are unsatisfiable and it should be easy. And as you can see from the bottom plot, looking at how difficult these instances are to solve, as we add labels, things get easier. Same thing for Christine Solnon's solver. And then one of the connectivity-based solvers. This is interesting. As we are adding labels, connectivity-based solvers find problem instances that should be trivial hard to solve. This might come as a surprise. This seems counterintuitive. It turns out this is important and this has a lot of real-world implications that I won't go into. The answer is connectivity algorithms are really, really stupid. So suppose I give you this pattern on the left, this target on the right, and I'm using colors for labels. And I don't know how clear the colors are, but that is a green vertex on the left, and that is a yellow vertex on the right. Okay, so obviously unsatisfiable. What a connectivity algorithm will do is it will map the red vertex to the red vertex, and then it will only look at neighbors. So it will try every possible permutation of mapping blue vertices to blue vertices, and only after has it tried them all will it go, oh, look, I can't find anywhere to put the green vertex, and it will backtrack. Whereas a constraint programming solver will say, okay, the red vertex is fairly hard, it only has one thing in its domain, and the green vertex has nothing in its domain, and it will solve this without search. So this is the difference. And it turns out in practice, there are dozens of papers where people will write preprocessors to try to avoid calling a subgraph isomorphism solver. And the argument goes as follows. Okay, in graph databases, subgraph isomorphism is NP-complete. We want to avoid calling an NP-complete algorithm. So what I'm going to do is introduce some heuristics so that we can detect that some instances have no solution without calling an NP-complete algorithm. And obviously this is a good thing because NP-complete algorithms will find these instances hard. Yes, this doesn't make any sense at all. But there are a lot of papers that say this. There's kind of an industry in the graph databases community of writing these papers and showing, okay, we can avoid having to call VF2 on 20% of the instances, 21% of the instances, 22% of the instances. And they all neglect to mention that if they called a constraint programming algorithm, then every single instance is trivially solvable in their data sets. So be careful how you benchmark. Okay, back to search. I told you for value ordering heuristics, we should pick largest target degree first. And I showed you a plot that showed you, oh, this is 50 times better than than doing the opposite. It's 10 times better than branching randomly. But here's the thing. What if I have a whole bunch of vertices in the target graph with the same degree? Or if I'm branching, is a vertex of degree 10 really so much better than a vertex of degree 9? It's a little bit better, but is it so much better that we want to commit heavily to it and unconditionally say, I definitely think this vertex should go here? Possibly not. There's an old technique in constraint programming called discrepancy search, where you replace depth-first search with something that branches more randomly. We can see from this plot, I'll not go into details, but maybe it's slightly better on satisfiable instances, but a lot better on a lot worse on unsatisfiable instances. Again, this now is a scatter plot showing so runtime using discrepancy search versus depth-first search. This is a log-log plot. Every problem instance is represented by points, and points below the diagonal line mean it's better to use discrepancy searches. And you see, okay, discrepancy searches are solving a whole lot of instances that otherwise wouldn't have worked, but in general tend to be quite a bit slower. I will not go into details of why this is, but just to say that this is what the state of the art was in the constraint programming community I'm going to suggest an alternative now. Okay. Let's go back to have a random value ordering heuristic. Instead of doing a backtracking search for, what I'm going to do is I'm going to run a backtracking search for, say, 100 milliseconds. And then I'm going to stop. I'm going to remember all of the subproblems that I've explored so far, and I'm going to restart my search from scratch. And I'm going to efficiently, there is an efficient way of remembering, okay, I've already explored this part of the search space. I'm not going to visit again. I will not go over this algorithm. The algorithm is called two-watch literals, and it is a very nice algorithm, but it takes a while to explain. But the key point here is, rather than committing to assigning this pattern vertex to this target vertex, I'm going to try assigning a pattern vertex to a random target vertex, run my search for a bit, and if that doesn't work, I'm going to stop, start again from scratch with a different random value, and run my search again, and I'm going to avoid repeating work that I've already done. So you can see this algorithm is still complete because we're recording everything that we've done. It's just that we're restarting and adding in a bit of randomness all the time. Okay. Again, looking at satisfiable instances, the bottom line, random branching, the middle line, branching on degree, so the best heuristic we had, and the top line, branching randomly, but doing restarts. And you can see, reading across, random search of restarts is a factor of 20 faster than the best heuristic we had. So does this tell us all this research we did into value ordering heuristics was a waste of time and we should just branch randomly? Okay, here's a scatter plot on an instance by instance basis, looking either random search of restarts or looking at conventional search. And what we're seeing is we're solving a whole bunch of instances down the right-hand side, but we were not able to solve previously. But also we're taking some instances that we used to be quite quick at solving, and they're taking a lot longer. So although we are able to solve a lot of instances using randomness, it's also making our algorithm perform worse on a whole lot of instances where we used to be quite good. So the question now is, can we develop something that gives us all of the benefits of randomness and all of the benefits of having a value ordering heuristic? Okay, and here is, yes. Yeah, so we're not doing any close learning here. So the black instances are unsat. And you see there, all the black circles are kind of down the main diagonal. So what this is effectively telling us is, if there is no solution, we can do restarts sufficiently quickly that there is no visible runtime penalty for doing restarts. Yeah, the overhead of doing a restart every 100 milliseconds is basically zero, thanks to a lot of clever engineering from people. Okay, so this is where I will probably upset Kuldeep. Traditional view, value ordering heuristics define a search order over a search tree. What I want them to do is say value ordering heuristics define what proportion of the search effort should be spent upon different subproblems. Okay. And according to some people who know some statistics, if your solutions are uniformly distributed, then random search should do better than depth-first search. If our solutions are not uniformly distributed, the question is whether we can design a heuristic that allocates, for example, if we think that 90% of the solutions are going to be here and 10% of the solutions are here, can we spend 90% of the time looking in this search tree and 10% of the time looking in this search tree? This is the idea. Okay, and with a another large amount of hand waviness about assuming we're working in random graphs and so on. If we have a domain dv, I'm going to pick a vertex from its domain with this probability here. And the key points of this expression, if I have two vertices of the same degree, I am equally likely to pick either vertex. If I have a vertex of degree 10, I am twice as likely to pick it as a vertex of degree 9. And I'm twice as likely to pick that as a vertex of degree 8 and so on. And my justification here is to do with solution density and the expected distribution of solutions. That if I'm saying that it's twice as likely for a solution to involve a vertex of degree 10 as a vertex of degree 9, I should spend twice as much search effort in this region. Don't ask me why I'm saying twice as much. This is a bit suspicious. Okay, let's try it. This is looking at using the random search heuristic versus the conventional search heuristic without restarts. And what you see is the two perform effectively equally. There are some instances where one happens to tiebreak better, one where the other tiebreaks better. But here's the interesting thing. Comparing depth first search versus this probabilistic research with starts, we're solving a huge number of additional instances you can see down the right-hand axis. And we're never really that much worse than not doing restarts to begin with. So there are not very many instances above the diagonal line, and the ones that are don't tend to be very far above it. So the conclusion here is, take your value ordering heuristic, introduce just a very small amount of randomness into it, do very aggressive restarts, and remember portions of a search space that you've already explored, and you'll end up with an algorithm which is much, much better on satisfiable instances without having really any performance penalty at all on unsatisfiable instances. So I quite like this, because usually when you design algorithms, there is a trade-off to be made. You're saying, okay, I'm going to be better on instances with property X and worse on instances that don't have property X. Whereas here, really, there is no penalty to pay for doing this, other than that you have to implement it. And that's the hard part. So the randomness is on the value specifically, so which target vertex we're mapping to. So we decide on the variable, so the pattern vertex, the variable, and then we are randomly picking the target vertex. So these instances down the right-hand column, these are where we had a timeout without doing restarts. And with randomness and restarts, we're solving them without running into a time limit. Yeah, I can also give you the the cumulative plot. And we see here, going from degree, which is where we started, to the top line, which I'm calling solution biased search, we're over 100 times faster on satisfiable instances. Here's something else you can do. Our computers now are multi-core. We have lots of cores. Constraint programming does not tend to make use of more than one core at a time. What we can do is give every thread its own random seed and run the same algorithm on a whole lot of different threads. Whenever the threads restart, we're going to share between different threads their description of the work they've already done. We're going to synchronize this across every thread and then keep going on the restarts. So what we're hoping here is that the randomness will direct different threads to different portions of the search space. And restarting and sharing no-goods will let every thread tell every other thread, I explored this portion of the search space, you don't need to. How this compares to traditional threading approaches. Usually when people are trying to do parallel tree search, they do some form of randomized work stealing. So the idea is you run one thread on a search tree, and then every other thread will steal subproblems at random. There are a few problems with this. One is you have to have a lot of synchronization. It is hard to get randomized work stealing to scale past maybe 10 threads, because after that, you have to be checking, has somebody stolen my work? Has somebody stolen my work? Randomized work stealing also ignores search order heuristics. So all of this effort we've put into coming up with good search heuristics, we have to throw this away for randomized work stealing. The advantage of using restarts and sharing no goods is every thread is running completely independently, except when we do the restarts. So there is no contention between threads. There is no communication, no synchronization. So this scales to a much larger number of threads. You can even avoid contention on communicating no goods if you let threads restart independently and just add work to add no goods to a shared pool. There's a way of doing this in a way that doesn't introduce contention. So again, this is comparing sequential to parallel now. This is a 36-core machine. Points below the XY diagonal are faster. And you see we're getting a speed up here. This is a log-log plot, so we're getting a speed up of 20 plus out of this. Although we are losing badly in instances that take, say, less than 1/10 of a second to solve. So there are some overheads to starting this up. It's probably possible to reduce these overheads quite a lot through good engineering. But for hard instances, we can actually exploit parallelism. Yeah, so a speed up of 24.2 out of 36 threads. If we compare this to, for example, what the Sat community can do, they might be able to get a speed up of 3 out of 36 threads if you're lucky. So this seems like it might be worth playing with some more. I can even run this across 20 machines in parallel, so distributed rather than multi-core parallelism. So I can make the algorithm run 144 times faster by using 20 computers, each with 36 threads on them. I have scaled this even further. My ultimate goal is to get a speed up of 1,000 by using the entire cloud. We'll see if that's possible sometime. Okay, summary of everything I've told you, things that you might want to remember about algorithm design and implementation. If you want this to work, there are a lot of things you have to get right. You have to get your algorithm design right. Algorithm engineering is a whole big thing, and it's not really something we teach in universities. We teach software engineering courses, which are about how to write big pieces of code where you don't understand the requirements. We don't teach people how to write small, intricate pieces of code where the requirements are very precisely defined. Evaluating algorithms is difficult. If you want to write a paper saying my algorithm is faster than your algorithm, you can pretty much always pick a data set that will let you say that this is true. You have to be honest when doing this, or you have to be in a community where other people will force you to be honest. Take your pick. The Sat community runs a competition every year, which has lots and lots of very strict rules because people really care about winning this, so people will try and cheat at it. If you're looking for an example of how to design a competition, it's maybe a good place to look. Although there are also arguments to be made that we are overfitting solver design to existing benchmarks. Certainly, if you don't have enough good benchmark instances, then benchmarking can really lead you astray into how you're designing algorithms. In particular for subgraph isomorphism, in fact, most application instances are really, really, really easy, so it doesn't matter what you do. And then all this benchmarking on hard instances, yes, is getting us better solvers, but for the majority of applications, any algorithm will work. And the final thing is make sure you understand the hardware that you're running on. So take a computer architecture course, even if you think it looks a bit too boring and a bit too electrical engineering-y for a computer scientist. if you understand what branch predictors are and how cache misses work and things, it will make you a much better programmer. The other lesson, being clever is good, but it only pays off if you can be clever quickly. Being clever slowly sometimes works, but quite often makes you worse off overall. And make sure you're solving the problem that people actually want to solve. This is very common. As soon as a chemist comes up to you and says, I want you to solve this graph problem, make sure you understand what the problem is, because just because a chemist says subgraph does not mean that they mean subgraph. Okay, the rest of my slides are on research topics, so mostly on things that don't entirely work that I hope that in 3 or 4 years will be working. Are there any questions on what I've done so far before I move on to? Okay. Oh, that's it.
Oh, yeah, sorry. Since you're talking like engineering, I have a few questions that might be, I don't know. So what language is it written in? It's C, C++, Rust,
C++.
Haskell.
I'm in the C++ camp.
Right. And what kind of, like, what do you use for checking things that like cache miss or like, so, I mean, there are a few tools like Valgrind, Perf, there are a few others. Like, what are your preferred ways of like figuring out that something?
Yeah, so my preferred tool by far is Perf. For those of you who haven't seen it, it's a Linux utility. You run a program in perf on trace mode, and then it will give you an assembly code dump of where you're executing, and it will highlight the lines where most of the time was spent during an execution. So it turns out for subgraph isomorphism, something like 90% of the execution time is spent propagating adjacency constraints. So perf lets you drill down to the machine code instruction level of what exactly is the processor doing, why is it taking so long to propagate this adjacency step, and you'll see, okay, it's for example, it's cache misses. So, okay, you can start doing prefetching, or you can change the layout of your data structures to improve memory performance. But yeah, perf is by far the most useful tool I found for this.
Same here. Yeah, okay, makes sense.
Yes, so perf will tell you about branch prediction statistics as well. Yes, at least on Intel processors. Perf is hardware dependent, so you can't run it on ARM Mac processors, for example. And I have found modern Intel processors give you more accurate statistics than AMD processors. But yes, you can get branch mispredictions, yeah. Okay, the fun stuff. Symmetries. Suppose I tell you to search for this pattern. Do you see this pattern has a symmetry? That C and D are interchangeable. What I claim is, if I want to find out whether or not this pattern exists, I only need to look for solutions where C is less than D. Because if a solution exists where C is greater than D, I could just swap the assignment of C and D and we'd be back to a solution. So you might look at this and think, okay, this C is less than D constraint would make the solver run twice as fast because it has half as much to do. It's not twice as fast. It's not that simple. But in general, if we have symmetries in either a pattern graph or a target graph, we should be able to make the solver run faster. Now, there are a few engineering challenges here. One is in calculating what the symmetries are. This is graph isomorphism, which is itself a hard-ish problem. Although it turns out the graph isomorphism is so easy that, yeah, we might as well solve the graph isomorphism problem before we start. The next problem is the algorithm that turns symmetries into constraints is decidedly non-trivial. If any of you are working with symmetries, I'd like to take the opportunity to plug somebody else's code here. There is a new library called Deja Vu, which you can find at automorphisms.org, which implements all the algorithms you need to do symmetry detection, and implements them cleanly without any dependencies on scary computer algebra packages. And the author is a PhD student who is looking for people to collaborate with in exchange for getting his name on a couple more papers. So he is very receptive to adding things to your library. So if you are ever solving anything with symmetries, this library is very much worth looking at. Hopefully in a year or two, I will have this integrated into my solver and you will actually be able to download and run it. Yeah, what about arbitrary symmetries and symmetries in both the pattern and the target graph? This is where you have to be a bit careful. I can explain to you an algorithm for eliminating symmetries in the pattern graph by getting less than constraints. I can explain to you an algorithm for eliminating symmetries in the target graph, which will give you some occurs less than constraints. It is not necessarily valid to eliminate both pattern symmetries and target symmetries simultaneously. It could be that you remove all solutions that exist if you do this. There is a way of making these interoperable. It's not easy. This is why this is on the research challenges slide rather than on the things that are implemented slide. Another interesting question is dynamic symmetries. So suppose my target graph doesn't have any symmetries, but then I delete some of the vertices because I know that certain values don't occur in any domain. Can I recalculate the entire symmetries of the target graph conditional upon what I've done so far and introduce new constraints? So here we're talking about speeding up a solver by potentially solving a separate NP-complete problem at every step inside search. Whether or not this is crazy is an open question. I believe this might be possible to do efficiently. Okay, counting and sampling. If you have a constraint programming solver, you can easily get it to print out every solution. It's just whenever you end up finding a solution, you print it out. So every domain has exactly one value. You print out the solution, and then rather than stopping, you just keep going, you backtrack and you find something else. What if instead of a list of solutions, I only want you to tell me how many solutions there are? Is there a way of doing this that is faster than just enumerating every single solution? And this is kind of an open question. And what if I say, okay, just give me an approximate count? So for SAT solving, Kuldeep can tell us all about how to do this efficiently in practice. Is it possible to steal all of his hard work and put it inside a subgraph isomorphism solver? I believe the answer is probably yes. Again, there's quite a bit of engineering work, and we'd need to make sure that the theory is valid. But I think this could be a very good thing for somebody to work on. And related to this is, suppose we want a few solutions but sampled uniformly. So a common application of subgraph isomorphism is in what's called a term rewriting system. So what you have is you have a graph that describes, say, the state of the world or the state of a chemical system. And you have a bunch of reaction rules. And a reaction rule says, find me a subgraph that looks like this and replace it with a subgraph that looks like this. And you want to run this over and over again for a certain number of iterations and see what state you end up in. And when you are searching for find me an occurrence of this graph, you want to do this uniformly. Now, constraint programming solvers will not find uniformly distributed solutions by default. If you say find me a solution, it will find you a solution with certain specific properties, but is quite far from pick me a solution at random. So is there a faster way of uniformly sampling a subset of the solutions, or probably uniformly sampling with, within certain tolerances? and doing this over and over again and repeatedly rewriting a graph and seeing where we end up? Again, I believe the answer is yes, and it is quite a lot of work to get this implemented efficiently. And then symmetries. Okay, what if I put in symmetry breaking constraints? I am eliminating most of the solutions, and then I say go and uniformly sample. How do symmetry breaking constraints interact with sampling? And can we cheat our way out of this problem? So can we sample when we have symmetry breaking constraints and then somehow rig the solution to pretend that we didn't have the symmetry breaking constraints? Again, I believe the answer is yes. Kuldeep also seems to think the answer is yes. This would be very fun to do. Proof logging. So right at the start of the day, I claim that my solver does not have any bugs in it. Or rather that if it does have any bugs, you can always detect them. Proof logging is possibly the most important thing that the SAT community has invented, possibly more important than SAT solving itself, is this idea that algorithms can prove to you that they have given the right answer. So what's the idea? Traditionally, we would have an input, we would run it through a solver, and the solver would put out a result. And we hope that the solver doesn't have any bugs, and the result is therefore correct. The difficulty is, what if we're using this result for something really, really important? For example, some of the research done at Glasgow University involves allocating kidneys to kidney transplant patients. And here it is, we're using an optimization solver to decide who gets allocated kidneys in a kidney exchange system, where there are policies set by the medical council saying how this allocation must be done. And of course, we trust, because we've done lots and lots of testing, etc., that our software is correct and the right people are being given the kidney transplants. But somehow, how can we be really, 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 really sure that we're getting this right if we're dealing with an application where potentially people's lives are on the line? Is there something better we can do? So here's the idea behind proof logging. Your solver doesn't just produce a result. Your solver must also write out a mathematical proof of correctness in a standard form that the solution is correct. And we take this result, and we take this proof, and we take this input, and we feed it into a proof checking tool. And this proof checking tool will either say, yes, your proof is okay, or no, your proof is dodgy. If the proof checker says that, yes, your proof is okay, then you can be absolutely sure that the result is correct. If the proof checker says, no, the proof is dodgy, you don't know for sure that you've got a wrong answer. It might be that you've got a right answer, but a bad proof for it. But you know that you can't trust that the result is correct. So you have to go back and fix your solver. But if the checker says yes, then we are safe. Now, the question here becomes, why should we trust that the proof checker is correct? And it turns out, actually, with a little bit of intermediate work, we can write a tool that takes a proof, simplifies it a bit, and turns it into something that is simple enough we can put it into a formally verified proof checker. So these are correct by construction software that is written to a mathematical specification using the whole system, so higher order logic. And we do have, for subgraph solving, this full process is now completely verified. So we have a solver that produces a proof, and we have a formally verified verifier. So now we know if we have a solution and the verifier says, yes, your proof is correct, we can absolutely trust that this is the correct solution to the problem. Okay, going back to thinking about graphs. What if the target graph is two separate components with no edges between them? What can you do? If your pattern graph is a single component, you can solve the two problems completely separately. What if your pattern graph also has two components? You can try finding the first pattern in the first component, first pattern in the second pattern in the first, second pattern in the second. Except what if the two components in the pattern get mapped into a single component in the target. I believe there is some inclusion-exclusion argument you can do to sort this out. I have not implemented this. I'm not confident I understand the maths well enough to implement this correctly. But if any of you are comfortable with inclusion-exclusion arguments and combinatorial reasoning, this could be a fun project. Yeah, and then what if the graphs are nearly two components? Can we cheat? Can we chop the graphs up, pretend they are two components, and then fix the solution? This is how some fixed parameter tractable algorithms work. They will say things like, if you only have one vertex that has a really high degree, you can remove this vertex, solve the problem in a bunch of different ways, and then glue everything back together again to get the answer. Could be worth trying. So enumerating or counting, yes. Yeah. Okay, close learning. So one of the big successes we heard about from stat solving yesterday was CDCL, so conflict-driven close learning. CDCL makes stat solvers millions, billions, trillions of times faster than conventional backtrackers. So we should be able to take some form of close learning and put this inside a subgraph isomorphism solver. And it should make the subgraph isomorphism solver millions or billions or trillions of times faster. I've tried doing this and it doesn't seem to work. Somehow the facts that we end up learning don't seem to be useful, that they don't seem to be reusable. I don't fully understand this. Again, if somebody wants an interesting, hard problem to work on for a year, with no consequences if you don't get anything, then I think this one could be a really fun problem, because if you ask anybody in the SAT community, they will tell you, oh yeah, close learning should be really, really good for subgraph finding. This is the kind of problem where close learning really excels, and yet it doesn't work, and we don't know why. Okay, I told you earlier about mapping degrees. So I can't map a pattern vertex of degree 5 to a target vertex of degree 4. When I told you about neighborhood degree sequences. So if my neighbors have degree 432, I can't map to a vertex that has neighbors 4222. Okay. What about directed graphs? So we can start reasoning about the in degree and the out degree of vertices. So a pattern of in degree 3 can't be mapped to a target vertex of in degree 2, and so on. What is the neighborhood degree sequence equivalent of this rule for directed graphs? And can it be calculated efficiently? I'm 90% sure I know the answer to this, but I haven't written it out formally. And then what about if we have labels? So for example, if I have 2 carbon neighbors and 1 hydrogen neighbor, I can't be mapped to a vertex that has 2 hydrogen neighbors and 1 carbon neighbor. So what is the general rule in this case? And can it be computed efficiently? Automatic configuration. This is another one. So I received an email a few weeks ago from somebody, a mathematician, who said, hello, I've been using your solver and it runs hundreds of times slower than my code I wrote in MATLAB to do the same thing. Am I doing something wrong? It turns out he was searching for a pattern graph which had 1 edge and 1 isolated vertex in a target graph that had thousands of millions of vertices. And if you're doing this, you should write a simple for loop that looks at over all of your edges and checks. You should not be calling a solver for something this small. The same thing, what if you feed in a triangle as a pattern graph into the solver? There is a really efficient algorithm for detecting whether a target graph has a triangle. We should run this rather than running my full subgraph solver. If you give me a large clique, we have better algorithms for clique than for solving subgraph isomorphism in general. This one, the solver does actually do. It will say, aha, I have detected the user has given me a clique. I am just going to run a clique solver. Except then you have to be careful. What if we're dealing with a labeled problem? Okay, then we can't do this. In general, it would be nice to have a solver that automatically detects that the user is giving it a silly input and switches its behavior to a much faster algorithm. Somehow this is a sort of thing that's very important for people using the software, but is completely impossible to publish. Maybe that's why we don't have it. And then I told you about these supplemental graphs. I have a hard-coded list of supplemental graphs that seem to work well on most graphs in practice. Really, we should have something clever to dynamically pick which graphs work, which shape graphs work on an instance-by-instance basis. And similarly, for example, if you give me a graph where all the vertices have the same degree, then neighborhood degree sequence reasoning isn't going to be very useful. So we should detect this, and we should not run it. And in general, making a robust algorithm for these kinds of inputs is a really interesting engineering challenge. But unfortunately, I don't think people put enough attention into. Pre-solving. So we saw that algorithms like RI are much, much faster on really easy instances. Maybe we should run RI for 0.1 of a second before we start up the constraint programming solver. Should it be 0.1 of a second? What's the magic number here? Again, engineering questions. The other thing here is RI is also very fast if you're solving enumeration problems, and there are huge numbers of solutions. So if there is a solution pretty much everywhere you look, then these problems come down to who can print out solutions faster. And RI can print out solutions slightly faster than we can. So again, how do we detect we're in that situation and switch to a faster algorithm if we are? Performance portability. This is an interesting one. I spend all this time implementing bit parallel code and threaded search. I benchmark on Intel processors because we have an Intel cluster. We have just bought an AMD cluster. Some of the optimizations I made that were clearly the right thing to do for Intel processors are not the right thing to do for AMD processors. I suspect that if ARM takes off, thanks to Apple, this will be even worse. We either need a way of writing high-performance software that is portable across processors, or to write different bits of code for different processors. I don't know what the good solution here is. For threaded search, this is even worse. Modern Apple processors and some Intel processors have two different types of processing core on them. They have these performance cores and these efficiency cores. Should we be running our solver on both performance and efficiency cores at the same time? My solver currently actually works better if you only run it on performance cores and tell it not to use the efficiency cores. So you say turn off half of the cores and the solver runs faster. Again, this performance and efficiency cores didn't exist 5 years ago when I designed the threading algorithm. How can we design and implement algorithms that are robust to these kinds of changes? Final research topic: design a file format for inputs for graphs. There are a lot of file formats for graphs. Every single one of these formats is bad. I could go on at length about this, but in general, if, for example, your file format gives a list of edges, if you have an edge from vertex 1 to vertex 2, does this mean there is also an edge from vertex 2 to vertex 1 or not? For a lot of these formats, there is no way of telling whether you're dealing with a directed graph or not, and you have to know, based upon context, whether you're going to get edges in both directions. Another example, the standard file format that a lot of people use, the top of a graph tells you how many vertices you have and how many edges you have on the first line, so you can allocate memory. The edges count. If you have an edge from A to B and from B to A, does that count as one edge or two? Or does it say that you're going to specify Does it tell you the number of lines in the file specifying edges? Benchmark instances on this are wildly inconsistent. And there are published papers of incorrect results because they are trusting the number of edges in the count and then reading it wrongly. The only thing you can do is ignore the edge count. And then you want the format that supports labels on vertices. Okay, what should the formats be? I mean, I kind of joke about this, but we do not have a good standard file format for describing a graph that tells you, is this a directed graph or not? Does this have labels? Does this have loops? There is an XML format that does all of this, but it's XML, so it is automatically terrible. But seriously, if you can get this right, everybody will love you. If you get it wrong, you will add yet another bad graph file format to the list, and you will make everybody's life a misery. I think I will stop there for this part of the work. Questions? Yes.
Yeah. For the degree sequence and the labeled version of it, isn't a natural generalization of the notion of degree sequence just this tuple? If you have a set of labels, say 1, 2, 3, and labeling the vertices of a graph, then for every vertex, you just look at how many labels, how many vertices there are of label 1, label 2, label 3, and so on. So there's a natural tuple that you can associate, and then instead of the degree sequence being a sequence of numbers, now it's in a sequence of tuples or a certain partial order on them.
Yes. And then for neighborhood degree sequence, the question is how you determine compatibility between two sets of tuples.
I mean, like this degree sequence is like a color. You can kind of associate with any vertex. So I mean, in the next level of the coloring, if you will, I mean, these sequences, now you keep multi-sets of these sequences.
Yes. So I think the answer that you're working towards is that it's a matching problem between these tuples.
Yes.
Yes, I think that's the answer, but I'm not 100% sure.
Oh.
Yeah.
It's like replacing the number 4 by maybe AB. What are those 4 neighbors?
Yeah, and then determining compatibility between two sequences. Yes.
Right now, we check whether one number is less than or equal to the other. We'll have to see if one string is whatever. Maybe if they're written in a lexicographic order, then there's something else, a subword of something else.
I believe you can. So for degree, you can write them and you can write your degrees in lexicographic order and compare. If you have in degree and out degree already, I think that stops working. But you can't just sort and compare. But I believe you can create a bipartite graph and do find a matching between compatible vertices.
Yeah.
I think
something like that.
Yes, something like that. So somebody needs to sit down and prove that the intuition is actually correct. Yeah.
You have more questions?
Yeah, just one. So there's, I mean, there seems to be, I mean, if you knew some things about these graphs in terms of, I mean, there's one area which I don't know, maybe you're looking at, or which certainly can be looked at, is looking at graph parameters.
Yeah.
So if you knew certain things about the graphs that you're looking at, that they have some kind of parameter, structural parameter which is bounded, then that could somehow be quite helpful. For example, so for example, if you knew that the graph is tree width something, fixed pattern graph, then of course there's a completely different way by which you can do the subgraph isomorphism, because you can just take the pattern graph and first decompose it, get its tree decomposition.
Yeah.
That you can do in linear time. but with a constant that depends on the tree width.
Yes.
Probably, I don't know how large that particular constant is. Those details need to be seen. But if you so you can just take the target graph and linear time produce a 3D composition, and then checking whether the pattern graph is a subgraph of this. It just amounts to checking a first order sentence over the 3D, over the graph, which just translates to checking it over the 3D composition. And then there's just a bottom up algorithm, linear time algorithm to do this. So in linear time, then if you knew that the pattern graph had, certain bound on its size, say, and if you knew that the target graph had certain bound on structural parameter, then you eventually have, at least in theory, a linear time algorithm to do this. Now, how well that translates in practice, it's not known, but this is something that comes to mind.
So I've had a look at these. The issue is even graphs of relatively low tree width. The relatively low tree width might be, say, 20. And then when your constant factor is 2 to the 20 in front of the algorithm, that's not something you want to run. And there are some interesting things here. There are some structural results. There is a result along the lines of if you have at most k vertices of degree at most k, something like that, then this is solvable. And one of the interesting things about the algorithm is it basically says chop the problem up in a particular way and then do an exhaustive search. And the proof is that the exhaustive search doesn't get too big if you branch in a certain order. What you can prove is that actually the branching order used by constraint programming solvers is at least as good as the branching order used in these FPT algorithms. So in some situations, actually, the solver is already behaving in an FPT manner if you happen to give it these FPT instances without it explicitly realizing this. But of course, in practice, we don't hit these worst case upper bounds, or rather the instances where we do hit them, we just can't solve them either way. So, yeah.
These could then be alternate proofs for these FPT results, or kind of statistically different alternate.
I mean, there are very few FPT algorithms that have been implemented and run successfully. Stefan Seider's group have a paper where they have done this. And the amount of engineering work taken, they're using database systems to store things on subproblems, that sort of thing. It's not easy. And how do I put this? I am skeptical that FPT is useful as a scientific approach for solving hard problems. I believe the FPT hypothesis is empirically false. But it doesn't describe why algorithms work well in practice, and it doesn't give us a way of characterizing what instances people find easy or hard to solve. That's where I am with that.
I was going to ask you that just the way you did the study with varying P, did you also do a study with varying any of the FPT parameters like tree width of at least the pattern graph, that where the hardness lies?
No. So I've done this with various graph generators, things like regular graphs. I have not tried generating instances of varying tree width and seeing how the solver actually behaves on them. Is there a way of generating instances with a given tree width at random? I guess you could start with a tree and then turn it back into, yeah.
I used to saying, is there a way to generate graphs of tree width given a given number, random graphs of a certain tree?
So so I give you a tree width and I want you to generate a whole load of random graphs with that tree width.
I would think so. There will be some studies there. Yes.
Okay. Yeah, okay. Maybe. The question is whether this gives you interesting graphs then or not. Yeah.
Yeah.
Yeah, that's a tricky one.
Well, I mean, you could use the general definition, this partial K-tree definition of tree width. So you start with a clique of size K, and then you're, or let's say K plus 1.
Yeah.
And then you start to add vertices in order. But then whenever you're adding a new vertex, you choose a subset of size K to connect to.
Yeah.
Or subset of size at most K to connect to. And if you do this randomly, then uniformly at random, then probably you are generating over a sequence of iterations, you're generating random graphs I mean, you're generating certainly graphs of bounded tree width at most K, and this is also a random process. So maybe I don't know what is the distribution, but certainly it is some random process which gives you graphs of tree width K for sure.
Yeah, so I suspect the solver would immediately pick out, hey, you've got this clique. I need to map this to this clique in the target graph, and then take it from there. Yeah, that could be. Yeah, I don't know how the solver would perform in those instances. It could be interesting.
So I want to ask about your proof logging.
Yep.
Maybe you can go to that slide.
Yeah.
Okay. So let me just ask, what do you have to trust here? So certainly you have to trust the verified checker,
Yes.
but you don't have to trust it because it's verified. What is it verified with?
Okay, so our verified checker is written in CakeML. So Hull, it's so the verified checker is written by Magnus Myrene and Yongkiem Tam. So it's the same trust base as the verified DRAT checker.
Okay. So do you write it in whole and then it generates code, or
so the
did
way
you do a
yeah,
deep
so the
embedding
way
of the code, or how do you do that?
so this is all CakeML. So you write the specification in Hull, and then as I understand it, this generates some code, and then you iteratively refine the code until you end up with something efficient that provably does the same thing as what it started with.
But then do you have to trust that refinement code?
So CakeML is itself fully verified in Hull. So the trusted base for this is, there's a couple of things. You have to trust the 30 lines or so of Hull code that everybody has inspected. And you have to trust that the 2 lines of Hull where we define what subgraph isomorphism is actually defines subgraph isomorphism.
Okay.
Everything else is fully verified.
So there's one other thing that comes up here though, which is how do you know that the thing you proved is actually the thing that was on the input?
Yes, so there is along with the definition of subgraph isomorphism, there is a very small piece of code that reads in the input file format. But again, you have to believe that this code interprets the meaning of your input file correctly.
Right.
Yeah.
All right, that's pretty good.
Yeah. No, this is all end to end now. The other interesting thing about proof logging is, so you would assume, okay, we're talking about subgraph isomorphism, so we have a proof format for subgraph isomorphism. Oh, no. This is all pseudo-Boolean proof logging. So nothing in the proof system knows what a graph is. We are able to prove all of the inferences that we do just using pseudo-Boolean reasoning. So we're not using a pseudo-Boolean solver, but we are doing pseudo-Boolean reasoning. So as I understand it, this is quite different to proof logging in SMT, where you have your proof structure and then all of your theories have their own formally verified proof systems.
No, that's not quite what we're pushing
Okay.
these days. So what we have is we have a proof format, which is actually a logical framework, which means you can define new proof rules. And so what the goal would be for each theory, you have to write a signature that contains the proof rules for that theory.
Yep.
And then you use those proof rules in the proof format, and then your checker will check that you use those rules correctly.
Right.
So you still have to trust those rules, unless you go one more step, which is you embed the whole thing into a proof assistant.
Yeah.
And then you prove the rules in the proof assistant, and then you reconstruct the proofs in the proof assistant. So we're actually exploring both of those directions. But yeah, it's quite a bit hairier because every theory, and not just every theory, but every implementation of a theory may use a different set of proof rules. So you have to somehow capture all.
Yeah, so this is what we ran into with constraint programming, where we have all the propagators. And what we found is we can justify the propagations done by every single constraint propagation algorithm we know of, and every subgraph finding algorithm we know of, and so on, just using 5 different proof rules. So cutting planes and an extension rule seems to be sufficient. So
yeah, I don't think it's quite that simple because theories can be wildly different, right? I mean, they can have different signatures,
but yeah.
different anyway.
Yeah, no, it's an interesting one though.
Okay, so I guess we conclude for now, and then there'll be the final session.
Final
the
session, yeah.
hands-on session.
I could give you a preview. I can tell you what we're going to do. I am going to give you a bunch of graphs, and you are going to try and find the maximum clique in as many of these graphs as you can. Some of these graphs are small enough that you can do them on pen and paper. Some of them are fairly hard. You could write your own solver. You could use an SMT solver following on from yesterday. Anything you like. I would suggest that you don't just download my solver and run it on them because that will be too easy. And I suggest you don't Google the instance names because you'll find standard tables of results. But yeah, I thought I would give you all some clique instances, and I am interested as to how far you can go with them. So I'll put those up on so that you can get started. We can have coffee. No, I don't have internet access. If any of you have internet access, github.com/KieranM. And I have just created a Sat+Smt school repository that has, here we go. So github.com/KieranM/sat-smt-winter-school. I have a whole lot of problem instances, and if you start by picking, for example, random 5, 5. So I'm telling you this is a graph with 5 vertices in it. Vertices are numbered 1 to 5. There's an edge between 1 and 3, 2 and 3, 2 and 4, 3 and 4, 3 and 5, 4 and 5. And I believe the maximum clique in this one has 3 vertices. So your challenge is to try and solve the rest of the instances in that repository. And if you solve them all, I'll make some bigger and harder ones. And yeah, coffee. Thank you.
Okay, so we'll start the final session of the day.
Yeah, so the plan was I have created a bunch of graph files for you. So the idea is you're going to try and find maximum cliques in these graphs. So remember, a clique is a subset of vertices where everything in the subset is adjacent to everything else. Some of those graphs have 5 vertices. They're easy enough you can solve the problem by hand. Some of them are bigger. The main thing that I am interested in is how far you can get coding up your own clique algorithm from scratch in an hour and a half or however long we have. I'd be interested to see what you can and cannot solve. You're welcome to use whatever techniques you like. You can write your own algorithm. You can use a SAT solver. You could just download and run my code and it will solve all of them, but that's not very fun. And who knows, if you start from scratch, you might come up with some idea that none of us have had before. So please shout at me if you have questions. Otherwise, I'll leave you to get coding. I think you're probably best starting from scratch. The graph files I've given you are in a very simple file format. So first line in the file is number of vertices. Everything else is just the edges. I mean, I could give you code that would read the file, but somehow, you know, it's reading in a text file. It's my solver is on my GitHub, and but I deliberately put them in a file format that my solver doesn't support, so you'll have to work slightly if you want to. So you'll have to write translation code if you want to.
I mean,